Okay, colleagues, welcome to the workshop Unveiling Hidden Physics Beyond the Standard Model at the LHC. We're very happy to see such a large number of registrants and also the fact that we have quite a broad geographical footprint where we have quite some interest also in Latin America, growing interest in Africa, Southeast Asia, and the Middle East. So very happy to see how inclusive the cohort of registrants are. So let me dive right into what we're going to be dealing with during this next 3 days, is to try to start answering the question as to whether we have exploited the LHC data to the fullest potential. And by that, we mean the data that we already have, run 1 and run 2, and of course, the future. Now, we are cognizant of the fact that there isn't such a thing as a magic wand or the one solution to all our questions, but rather we have a comprehensive ecosystem of ideas and tools that we want to exploit in order to start answering that question and come up with new strategies to find new physics at the Large Hadron Collider. Of course, we always have to be driven and guided by theory and phenomenology, fields, interactions, symmetries, and broken symmetries, and that always has to be there to guide us along the way. Anomalies are also very important in that whether they are there or ultimately will be resolved, they still can help us develop model building in order to attack the problem of hidden signatures at the LHC. In recent years, machine learning has really enhanced our ability to add intelligence to our search strategies, and it allows us to introduce intelligent algorithms with less dependence on modeling. While it should still be guided by our theory and phenomenology, it allows us to reduce model dependency. So that's extremely valuable as well. And last but not least, as you know, there's already an open discussion regarding the availability of partial data, which opens a new conversation about the use of data in a broader context. We're here not really talking about the ability of individual physicists to find hidden bumps and all that. That's not what we're talking about here. Experiments should still be should lead the way towards discoveries, as they are an irreplaceable repository of knowledge of the detector and systematics. But this we want to view more as a platform or as an additional tool to enhance the communication between theorists and experimentalists and bring that conversation to a qualitatively new level. So in that light, let's go quickly through the structure of the workshop. So Oliver and me thought the way to go here is, instead of having many presentations, have a reduced number of presentations with sufficient time for discussions. We'll have our first speaker, Nima, who will go through the theory landscape, followed by 2 presentations by Bhupal and Andreas that will cover the status of anomalies, where Bhupal will focus on the overall picture of anomalies in collider and outside collider physics, and Andreas will focus on the possibility of the possible lepton flavor universality violation. That will later tomorrow bring us to 2 presentations by Susanna Martin regarding hidden signatures and the model behind. And after the break, we'll have a comprehensive view of machine learning as a tool in this context. And that will lead us to the 3rd day, March 3rd, where we will have a discussion about open data access with 3 very important presentations by Eckhart, Tibor, and Philip from 3 different perspectives in order to understand what that means. And the panel discussion will be the workshop will be closed by a panel discussion by very prominent members of our community who will focus on the issue of how to use these tools in order to enhance the ability to communicate between theorists and experimentalists. theorists. Now, even though we've designed the workshop so as to get enough time to discuss, there's never enough time for discussion. And that's the reason why, in the interest of inclusivity and people engaging in conversations during breaks, during the workshop and after, we've created a forum discussion. So we strongly encourage you, please, to follow those discussions at the Mattermost web server at CERN. Before giving the floor to Oliver to introduce the first speaker, we really want to thank the International Organizing Committee, which is made of very prominent members of our community, for their great work, invaluable advice over the past few months in order to shape the structure of this workshop to have its biggest impact possible. And last but by far not least, given the fact that there was quite some interest and a large number of participants, we need support. So we really want to thank the Liverpool Itemba Labs, Leeds University teams that have made the organization of this workshop possible. So without further ado, I will give the floor to Oliver to present the first speaker, and so that we can carry on with our agenda. Thank you very much.
Okay, thanks, Bruce. Also, welcome everybody from my side. I don't think I need to introduce him very much. He's very well known. So Nima, if your slides are ready, you can start sharing any moment.
Thank you. Can you let me share my screen? Also share video. Start my video, actually. Can you guys see my screen okay?
Yes, the slides on screen.
And let me see if I can. Can I also share video, or do you just want the audio?
You can show your face if you like.
Well, it says I can't start the video because the host has stopped it. That's fine.
You should be able to start.
There we go. Just to make it slightly more human. All right. Oops. Okay, great. All right. Well, I'm really delighted to be able to join this meeting, even if virtually. And let me just apologize ahead of time. I've been having some terrible difficulties with my Wi-Fi connection. So if I drop out once, just give me a few moments and I should be able to come back on. All right, what I'd like to talk about are associated with the theme of this, what promises to be an exciting meeting, are motivations for new physics just around the corner. And I think there's a sort of a narrative, a general narrative that I think it's worth confronting head on. I think there's a sort of an anti-particle physics narrative that's out there, partially even within some people in the particle physics community, that takes stock of the situation that we're in here in the year 2021 in the following way. That 40 years of speculation about what we might see beyond the standard model by beyond the standard model theorists were just full of crap. And that we expected and predicted and said there would be all these new particles at the LHC, and we haven't seen that. And we're all shocked. All the theorists are shocked that there's only the Higgs and nothing else at the LHC. And the notion of naturalness that seemed to promise this cornucopia of new particles beyond the Higgs was complete bullshit. And that related to that, all the reasons for seeing new particles, either at the LHC or beyond, have totally evaporated. So that's, I think, a narrative. It's not an entirely uncommon narrative. And it has some elements of truth to it, but I think it's essentially false. And that's what I want to really stress in this talk. First of all, the failure of the sort of perfect notion of naturalness is not a surprise. It's something that was anticipated by many theorists long before the LHC. There are hints for it in data long before the LHC. I would say it was not a majority opinion among theorists, but it was the opinion of a solid minority of theorists, certainly including me, but also many other people before the LHC turned on. And what's happened so far with what we've seen at the LHC, discovering the Higgs and nothing else, doesn't make the mystery of the origin of the Higgs mass and the weak scale go away or become irrelevant, that it's only become more difficult and a deeper question that's likely connected to other deep questions in fundamental physics. What I'd really like to talk about more specifically is that there are decent to good theoretical motivations. Definitely not 100%, definitely not no loose theorems, but not in the opposite direction either. There's like zero reason to expect that there's anything in the next sort of decade of energy or so, that there are good theoretical motivations for new particles around the corner. And I want to begin with what I think of for myself, I mean, still today, as my best bet for what's going on with TeV scale physics. And it's a picture of the world that at least I came to sort of, if you woke me up in the middle of the night, put a gun to my head and ask what I think is going on. This is what I would have said is going on since the year 2004 and 5, so many years before the LHC turned on. So since then, my own best bet has been an unusual picture of supersymmetry that's given by the minimal version of split SUSY. And nowadays there's like over 1,000 papers on the subject. But when I was first went around giving talks about this in 2004 and 5, many of my theory colleagues literally yelled at me at conferences because of this heresy of talking about a supersymmetric theory that also had some fine tuning for electroweak symmetry breaking, maybe between a part in 10,000 to a part in a million in a conventional way of talking about what tuning is. The response to which was always that every theory we'd ever written down had a gigantic tuning for the cosmological constant. So whatever was going on with the Higgs was a tiny detail on top of that. So while the motivations had to do with tolerating tuning and maybe connected with the existence of a landscape of vacua and all this other stuff, it was a very concrete model where the scalars of supersymmetry were just 100 to 1,000 times heavier than the fermions for good top-down reasons about how easy it is to break supersymmetry in that particular way. The motivation for having any particles at the TeV scale came from the simplest picture of WIMP dark matter, which would be electroweak ENOs or Higgs ENOs in the 1 to 3 TeV range, which are not made at the LHC and for very good reasons not seen in direct detection experiments, simply because their cross-section, for no malice, no reason of moving the goalposts or changing the theory after data, the cross-sections were just tiny, and there's a very good reason that we haven't seen them in direct detection. This class of theories correctly predicted that the Higgs would be between 120 and 135 GeV. It's a very mild prediction, but at least it's not wrong. And it's still conceivable that the gluino of split SUSY might be in the reach of the LHC. Might not be. That was, again, totally clear in the year 2004, 5, 6. Again, before the LHC, that in a decent chunk of the parameter space of minimal split SUSY, you wouldn't see any new particles at the LHC. In a decent chunk, you would. But if this picture is correct, both the electroweak ENOs and the gluino should be seen at 100 TeV collider. So that they're not, up the Planck scale. They are just an order of magnitude. The next order of magnitude reach beyond what we can get at the LHC would be sort of sure to cover the parameter space where we'd expect to see new particles in these models. And this is really an important point. It's not like we could say if we didn't get to 100 TeV that, well, maybe it's there at 1,000 or 10,000, 100,000 TeV. You can't keep pushing the scale as arbitrarily heavy in this picture without, for example, ruining the prediction for the Higgs mass. And something else that we can wait for in this class of ideas are electric dipole moments, which have the measurement of electron electric dipole moments has been revolutionized over the past 10 years or so. And our atomic physics colleagues claim to be able to get another 2 orders of magnitude on the EDM, going deep into the territory where you might expect, if there's large CP violation in the supersymmetric sector in these models, to actually see something. So that's something to keep an eye on. All right, so that as I said, that continues to be my sort of 0th order picture of the world, but we're not religious in particle physics. We care about data, and it's definitely interesting to continue to think about alternatives. So here's another picture that we talked about with some friends about 5 years ago. This is the idea of naturalness. I won't go through it in much detail, but the rough idea is that the standard model is not alone, that there are lots of sectors, many, many copies of something like the standard model, and the Higgs mass squared parameters just randomly varies from sector to sector, and so therefore if there are n copies, there's one naturally where the Higgs mass squared is whatever the naturalness cutoff scale, capital lambda squared, is divided by n, simply because there are n sectors. And then there's a cosmological reason that only the bottom of the spectrum, the lightest particles, are reheated. So that's why we find ourselves made out of that sector that seems to be this factor of n down from the cutoff. Now, in this picture, there's naturally a limit on n. Because if you have n species, there's a renormalization of the Planck scale that grows with n. And so the actual ultraviolet cutoff of the theory comes down as n gets larger and larger. Now, we have some indication of an ultraviolet scale near the gut scale. And so if we don't want this cutoff scale to come much further down than the gut scale, that limits this n not to be bigger than, let's say, between parametrically and Planck squared over m gut squared, and something between 10 to the 2 and 10 to the 4. And so if we care about the gut scale because of, for example, the supersymmetric picture of unification, then that tells us that the actual supersymmetry scale would be up from the weak scale by exactly the same factor, the square root of this ratio. So it would have to be less than about 10 TeV or so. And in this picture, it's not 100 TeV or 1,000 TeV. The actual sort of superpartner scale would be expected to be 10 TeV, and also not the weak scale. Okay, so this little bit of fine structure up near the Planck scale, between the Planck scale and the gut scale, will be reflected down around the weak scale, between the weak scale and the sort of 10 TeV scale where we'd expect to see the rest of the superpartners. And if the superpartners are at 10 TeV, then the lightest of them could naturally be close to a TeV. For example, the right-handed Tau in many examples could be expected to be close to the TeV scale. All right, so those are two examples that have been talked about already. In both of these examples, there isn't a particular reason to see something literally around the corner. For example, something that the high-Lumi LHC would care about. It motivates that we could see something just in the next decade of energy, but not necessarily literally around the corner. So what I'd like to talk about in the rest of this talk are two pictures for what might be going on associated with the origin of the weak scale, where there are good reasons to expect something accessible soon. Okay, and the first picture has to do with some very sort of deep structural theoretical issues, which, however, I don't yet know how to convert into a very concrete theory. But I want to give you some sort of cartoons of what such a theory might look like. And explain why it would lead to a prediction of sort of order 1 deviation, of large deviations in Higgs couplings, which we could be sensitive to even at the high-Lumi LHC. And the second is a totally different set of ideas. It's just a concrete model with a different picture for solving the hierarchy problem, correlating it with the solution of the cosmological constant problem. So this goes by the name of the weak scale as a trigger. I'll explain what that means. In this picture, we're forced into a very particular limit of a 2 Higgs doublet model for electroweak symmetry breaking, where all the Higgses are forced to be light. There's no way of decoupling them to make them heavy. They're just forced to be light. And it's rather remarkable to me that this limit is not yet ruled out by experiment, but it is totally within the wheelhouse of the high-Lumi LHC and massive signals for a Higgs factory. So these are the two things I want to talk about. And I'll probably spend a little bit less time talking about the first one and a little bit more talking about the second, but I want to give you a flavor of the sort of different things that at least I've been thinking about related to these issues. And just to put things in a little bit of context, and to emphasize the sort of drama of the questions that are involved, especially since we've seen the Higgs and nothing else at the LHC. I just want to remind you that for nearly 400 years, fundamental physics has been on this march of reductionism and a march of symmetries, which makes it all the more remarkable that where we are now in the 21st century is putting this basic strategy of the past 4 centuries under some severe stress. We expect, for example, that the very notion of space and time is doomed, has to be replaced by other principles, and associated with this, that the whole notion of reductionism, the sort of Wilsonian effective field theory paradigm, is fundamentally false. We also don't understand the answer to very simple questions like, why is the universe big? Why is there a macroscopic universe, even though there are violent quantum mechanical fluctuations at shorter and shorter distances? And these are big scale questions. They're not little details. They're big scale questions, and they indicate the need for really new ideas beyond the paradigms of space-time and internal symmetries. So, for instance, we understand why the photon is massless, and the photon stays massless because the interaction of the photon with all the virtual particles in the vacuum can't convert the 2 degrees of freedom of a massless photon into the 3 degrees of freedom of a massive one. And this is why gauge fields and chiral fermions can be easily engineered in condensed matter systems, for example, because their presence is robust for exactly the simple 2 not equal to 3 degree of freedom counting business. But what's special about the Higgs is that it has spin 0, and there is no difference in the number of degrees of freedom between a massless spin 0 and a massive spin 0 particle, and that's why we don't understand why the Higgs doesn't pick up an enormous mass and a huge inertia by interaction with virtual particles in the vacuum. In this way, the Higgs is special, and it does not naturally rise in condensed matter systems, unlike chiral fermions, things like chiral fermions and gauge fields, which do. So both the story of the Higgs and the cosmological constant are an indication that we have to go beyond symmetries that have been the most powerful tool so far to sort of control the nature of dynamics and interactions in a world governed by the rules of space-time and quantum mechanics. But the story of the Higgs already, as we've said, the difficulty is that there's no difference in symmetry. There's no difference in number of degrees of freedom, whether the Higgs mass squared is positive, 0, or negative. And similarly with the cosmological constant problem, there's no difference in symmetry between a world of positive, 0, and negative cosmological constants. So we don't have symmetry explanations for these extremely 2 fundamental features of our world that are responsible for the existence of a big world around us. If the cosmological constant was huge, the world would be curled up to tiny size. If the Higgs mass squared was enormous, we would all collapse into black holes. There would be no macroscopic structure. The reason for macroscopic structure is somehow tied up with a need to go beyond the paradigms of space-time symmetries. And both of these large questions of the emergence of space-time and the existence of a macroscopic universe are indicating that we're missing something huge about the quantum mechanics of our relativistic vacuum. And I want to stress here that the discovery of the Higgs is crucial for this, because it makes it clear that a relativistic vacuum is qualitatively different than anything we've seen elsewhere in physics, not just at the Planck scale, where we might expect some drama having to do with the end of space-time and all of this fancy stuff about quantum gravity, but already at the much closer to home at the TeV scale, where the basic analogy with condensed matter physics that goes into the Wilsonian effective field theory picture of the world just doesn't work. And that's the surprise of the fact that we've seen the Higgs and nothing else. Okay, so with that context, I want to make clear that the fact that we've seen the Higgs and nothing else is something dramatic, is something important, and in my view, it's something that likely needs a structural reappraisal of how we think about physics in order to figure out what it's actually telling us about the world. So let me say a few things about this idea of the UV-IR connection, the possibility of hidden symmetries, and what I'm calling transcendental tuning. So what is the UV-IR correspondence? This is a sort of a famous fact about quantum mechanics and gravity that has been appreciated for decades, which is the following. Ordinarily, in particle physics, we say that to probe shorter distances, we go to higher energies. But at some point, that logic breaks down because you end up putting so much energy into such a small region of space that you collapse the region that you're looking at into a black hole. And that happens for energies comparable to the Planck scale. And if you get frustrated by that and try to if you get frustrated by that and use even higher energies, you make an even bigger black hole. So high energies corresponds to long distances, not short distances anymore when energies get above the Planck scale. And amongst other things, this means that the entire ideas of reductionism and the Wilsonian effective field theory paradigm is essentially false. It's not true that the fundamental laws are given to us fundamentally at arbitrarily short distances, and then they sort of cascade down into long distances in the tower of effective field theories. It's nothing like that. It's likely far deeper and more radical, because super high energies turn into super long distances again. But this might make you think this only happens near the Planck scale. But there is an important feature to this, which I'm going to stress in a second, which is that since we know this Wilsonian picture is incorrect, it tells us that it's crucial to probe not only the on-shell Lorentzian properties of the Higgs, like we do, how we, for example, how it's produced and how it decays, but also the off-shell Euclidean couplings of the Higgs. And that's because the Wilsonian paradigm is fundamentally Euclidean. In fact, the standard picture of local quantum field theory relies crucially on this analytic continuation between Euclidean and Lorentzian signatures. But this interesting connection between the UV and the IR can radically change this. And we've actually seen elsewhere already examples of how the UV-IR connection can radically change this picture. And the interesting thing is that it can change it in such a way that even though the corrections are maybe coming from the Planck scale arbitrarily far away, they can give an order 100% change to what you might have thought of as a reliable low energy effective field theory calculation. So I want to give you an example of this. So this is a toy example, but in fact, exactly this phenomenon comes up in explorations of quantum gravity that people have carried out just over the past few years. So here's a toy example. Imagine an experimentalist has measured some quantity, F experimental of T, and it looks like 1/T. To very good approximation. Now, T is a time variable. It looks, so they've measured it for real time, positive time, and also they haven't measured it for arbitrarily short time. So there's some sort of UV scale that they haven't. That's the limit of their probe. So they've measured it. It looks like 1/T for T much bigger than TUV. All right. They announced this at their Morion conference, and the effective field theorist in the audience says, "Oh, I have a theory for what this function is." The function is 1/T, okay? And they say that I can actually then make an interesting prediction based on this function. That of course the experimentalist has only measured this for real times here, but the theorist says that this 1/T can be analytically continued to any complex value of time, and in particular, if you do a contour integral of this f of t around the origin, you're going to get 2 pi I. If you divide it by 2 pi I, you'll get 1. Now, this looks like a reliable quote unquote effective field theory calculation because it's being done on a huge circle, very, very far away from TUV. All right. So there's a reliable calculation, apparently reliable quote unquote effective field theory calculation that does not rely on super high energy physics, that does not rely on short time physics. Which makes it an apparently reliable calculation that this quantity is 1. Nonetheless, they could be completely wrong. And here's what f of t really is. F of t is 1 minus 10 to the minus 120 t over TUV divided by t. You'll notice that this function looks exponentially close to what the experimentalist has measured in the physical domain where the time is positive. But if you look at this, if you look carefully at this function, there's actually no poles at all as t goes to 0. And the contour integral, therefore, around on this big circle is actually equal to 0. Not equal to 1 is equal to 0 because of this exponentially tiny correction that is totally invisible to both the experimentalist and the theorist in the physical region. Okay? In fact, this is not some esoteric example. There's precisely this mechanism for removing what's known as the bulk point singularity in the ADS-CFT correspondence that actually it precisely explains why there's no such thing as local points in the space-time when you have a holographic boundary description of the physics. Now, what's going on here is that, of course, the assumption that the field theorist made that this function is analytic and you can blithely continue it for complex t is wrong, because in fact out here it grows exponentially instead of dying exponentially. Okay, so there is something suspect about the analytic continuation in time. And I can give you a simpler model for where this comes from. For example, the 1 over t could have come from an integral over energies of a phase, e to the I e t. And so clearly here, there's a pole at t equals 0 because this integral diverges as the energy goes to infinity. So depending on for example, if t has a negative imaginary part, this would blow up exponentially. And therefore, there has to be some kind of singularity at t equals 0. And this argument persists if at very high energy here, you change the behavior, but that things still fell off as a power of energy. The fall off of the power of energy is what we expect in local quantum field theory for correlation functions and all kinds of other observables. And if we have that kind of behavior, we don't change the logic of this argument because it's still true that there's a singularity when the imaginary part of t is negative and this integral diverges exponentially. But if the high energy behavior is instead gravitational, and this is something that we expect, for example, 2 to 2 scattering amplitudes when we have quantum gravity are expected to die exponentially as we go to high energies because they're dominated by the production of black holes, and the probability that a black hole decays back to just 2 particles is exponentially tiny. Then because there's an exponential suppression here, it doesn't care about what the sign of the imaginary part of time is, and so there's no singularity at all at t goes to 0, and in fact exactly the same integral is equal to 0 instead of 1. So you thought you had a reliable calculation, but something happening very far away at the scale capital lambda changes the result of the calculation by order 100%. Okay, so that's an example of this sort of UVIR correspondence. And if something like this is going on to explain the origin of the Higgs mass, and I don't yet have a very totally concrete model for it, I'll give a toy example of what a model might look like of this form in a second. But if something like this is going on, it's clear that what we have to probe is the Euclidean off-shell properties of the Higgs, because those are the things that might be modified by this UVIR connection. You see here, it was the continuation to complex time, which is the Euclidean continuation, which is suspect. There's something wrong with that. And that's what gives rise to this order 100% difference between expectation and the right answer. So it's crucial to probe the Euclidean off-shell properties of the Higgs. For example, it could be that we shut off the Higgs TT bar vertex when the tops get off shell by, let's say, 500 GeV. This is not a standard picture of compositeness. We wouldn't expect composite Higgs or composite tops. This is loosely some kind of mutual non-locality between the Higgs and TT bar. This is the sort of last stand of some kind of natural explanation for the Higgs that we can have access to at the LHC, but we know very little about this. We have a very, very few good probes of the off-shell coupling of the Higgs to TT bar. And there are 2 things that we could think about. There are perhaps others. But first, if we do modify the Higgs to TT bar coupling off-shell, we would expect some change in the rates for Higgs to gamma gamma and Higgs to glue glue, even though these things are dominated by the loops where the particles inside are close to on shell. There's still some contribution to them when the particles get off shell. And so you'd expect around a 3% modification to Higgs to gamma gamma and a 10% modification for Higgs to glue glue. This is, of course, absolutely perfect for a Higgs factory. These are huge signals for a Higgs factory, but it's also the targets of right around the things that we're going to potentially incisively probe by the high luminosity LHC. And also, even more directly, you would expect things like the TT bar Higgs cross-section to shut off when the PT of when the top here becomes off shell by more than a few hundred GeV. This is, I think, very difficult even for the high Lumi LHC, but it's potentially perfect for a 100 TeV collider to actually probe. Okay. All right. So that's a kind of a very 0th order picture that we need to check the Euclidean continuation because that's where something could be lurking, where something about this UVIR correspondence, even arbitrarily far away, has a chance near the Planck scale, has a chance to affect things right around right around the corner in an interesting way. Now, there's a more concrete model for this. I don't want to spend too much time talking about this, but just to give you just a very rough idea of what I have in mind. We're used to talking about the UV sensitivity and the hierarchy problem in the language of the ultraviolet sensitivity of the Higgs potential to the presence of new massive states. And so one way of saying it is if we had new massive states that couple to the Higgs, that we have a correction to the Coleman-Weinberg potential of the Higgs involving the massive states. And this is calculable. This is not one of those quadratic divergences that you can talk about whether it's philosophy, whether they're there or not. This is a calculable correction to the potential of the Higgs coming from these new massive states. It goes to their mass to the fourth log mass squared. And if you expand out the Higgs dependence on these masses, you get these huge calculable corrections to the mass of the Higgs. And so one way of talking about the hierarchy problem is why should the tree pieces that are sitting there already that don't have these logarithms in them, see these things have the logarithms in them that make them calculable. Why do the things that have the logs in them cancel against the things that don't have the logs in them? That seems crazy. That's something that's non-analytic and calculable should somehow conspire to cancel against something else which is rational. So normally we in fact talk about this sort of distinction between trees and loops as being things that are rational polynomials in the Higgs versus things that have logarithms and are transcendental in the Higgs. We use this as an excuse why we can't have a decent solution, why we can't have a conspiracy between these two terms. But in fact, exactly this is a reason we can have a conspiracy between them. And in fact, there are long known funny tunings in quantum field theory calculations. If you open up Peskin and Schroeder's book and look at the calculation of the lifetime of positronium, you'll find this interesting factor of pi squared minus 9 sitting in front of the whole thing. Now, pi squared minus 9 is accidentally a little bit small. And you might think, oh, it's just an accident that number is small. But in fact, no, there's not an accident. There's a mechanism at work that explains why that rather small number appears. And there are other examples of the same sort in B-physics calculations where you even get sort of 1 part in 100 type cancellations of this sort with expressions involving pi's and rational numbers canceling. There's a mechanism behind it. And the mechanism behind it has to do with rational approximations to transcendental numbers. So if you want to, here's an example. If you want to write the logarithm of 2, it's the integral 0 to 1 dx over 1 plus x. And the reason we get this interesting transcendental number here is that the integrand has a pole at x equals minus 1. If it didn't have a pole at x equals minus 1, we get something rational. But it's because this integral has a pole at x equals minus 1 that depending on whether on how we route this integration contour between 0 and 1, we can get answers that differ by 2 pi I. So that's why there's a sort of pi's worth of complexity possible in this answer. A logarithm can come out of this answer. And therefore, if you take the same integrand and now weight it with some polynomial of x, we know ahead of time that the answer will split naturally into 2 pieces. One piece that is transcendental, as is log 2, and another piece which is rational. The piece that's transcendental proportional to log 2, the coefficient will be the residue of this polynomial at x equals minus 1. Right? So no matter what this integral is numerically, it's written as a sum of 2 pieces, which are fundamentally different. They're sort of number theoretically different. One is a transcendental, irrational number. The other one's a rational one. So if you make this p of x, this particular simple polynomial, x1 minus x over 2 to the n, then you'll notice that p of x is actually equal to minus 1 when x equals minus 1. Therefore, this integral is plus or minus log 2 plus something rational. You know that ahead of time, that at any analytic computation is going to give you log 2 plus something rational. But on the other hand, x times 1 minus x over 2 is bounded to be less than 1/8 between 0 and 1. And so the left-hand side is bounded by 1/8 to the n. And so that means that if you only saw this integral, you would know ahead of time you get a tiny, tiny number when n is large. But if you evaluated it analytically, it would force to be expressed as the sum of 2 pieces that are large and cancel against each other to high accuracy. So there's a huge apparent tuning. Tuning here that gives us outstanding rational approximations to log 2. For instance, if you take n equals 5, then you get log 2 minus 2329 over 3360, which is around 10 to the minus 5. Okay, so if someone handed you this, you'd say, wow, what a coincidence that there's a huge cancellation between these two terms, but there's an obvious origin for that coincidence in the original integral representation. Okay, the same idea actually, just as a recreational statement, can be used to find rational approximations to pi, including in the simplest case, the famous 22/7, which is a pretty decent rational approximation to pi. And exactly this phenomenon explains the pi squared minus 9 in the positronium lifetime calculation. There are small phase-space integrals, which, however, when any analytic computation divides them into something transcendental plus something rational that cancels the high accuracy. And so there's a strategy for doing this for the Higgs, which is to find some computation for the Higgs mass. And there's a motivation for this that I skipped, having to do with recent developments and thinking about scattering amplitudes as the answer to very different questions involving the volumes of some abstract geometric spaces that actually expose hidden symmetries, even for simple non-supersymmetric theories, have hidden symmetries that we didn't know about before. And these hidden symmetries even tell you about better behavior than expected at very high energies, in particular directions in momentum space. So there's a loose motivation behind all of this, but the sort of concrete challenge is to imagine some calculation for what you will eventually interpret as the Coleman-Weinberg potential that involves an integral over the Euclidean region, but that there's a huge exponential suppression of what you think of as the contribution from the Euclidean region, while leaving all the Lorentzian poles unaffected, so that we're not screwing up the usual physics of unitarity and causality when we do this. That's exactly what we saw in this example, that the pole at x equals -1 was unaffected by this polynomial, but the rest of it was precisely such as to make the contribution in this region between 0 and 1 much smaller than expected. So that's the kind of thing that we want to see. And there's a toy example. There's a variety of toy examples. I don't have time to talk about it. This is actually a very simplest toy example that just picks up from the example that we just talked about, where you just put some tiny little modifications to the examples that we just talked about, which has a feature, though, that when you do the calculation, it splits it into two pieces. One piece with a logarithm in it that looks like a Coleman-Weinberg potential calculation, a legal Coleman-Weinberg potential calculation, and another piece which is rational that looks like what you would interpret as a tree-level contribution that's just sitting there already. And it's guaranteed ahead of time that these things will cancel against each other to very high accuracy. Here's a simple example. They're guaranteed to cancel to very high accuracy for the same reason that I mentioned before. Okay, so it's possible to see this at least at the level of toy examples. They're not complete theories yet, because we don't yet have a version of this idea that works for a totally general observable. We have versions that work for what looks like the sort of one loop Coleman-Weinberg calculation, but it does make it clear that, again, at least we see this sort of basic phenomenon as possible. That we greatly modify the Euclidean properties of the Higgs while leaving the Lorentzian physics that has to be correct intact. So again, it's crucial to probe the Euclidean properties of the Higgs in exactly the way I mentioned before. All right, so let me now move on to the second example quickly. Can I just have 10 more minutes? Is that okay?
Sure, you can have 10 more minutes.
Okay, great. Sorry, I forget what the official close of my. All right, I'll take 10 more minutes. Okay. All right. So now let's move on to the second idea. The ideas I talked about were very speculative and sort of cartoonish before. These are still, of course, speculative, but they're much more concrete. Okay. So let's talk about this notion of the weak scale as a trigger. And so we're going to start with a very simple question. What happens in the standard model as we vary the Higgs mass squared parameter? What correlation function in the standard model, what operators, what observables care about the Higgs mass squared? And well, the answer is totally obvious. The spectrum cares about the Higgs mass squared, most importantly of all. But notice that the question of the spectrum is not about the expectation value of a single local operator. It's not about some expectation value of O of X. It's instead about a two-point function, O of X, O of Y, or if we think about it in momentum space, it's like, for example, the pole of the propagator for the electron depends on the Higgs mass parameter. As I vary the Higgs mass parameter, if I imagine varying it, clearly the pole of the propagator changes. Are there any local operators which care about the Higgs mass squared? And the answer is essentially no, with one exception that I'll talk about. And this is a nice way of thinking about things because it's in fact a sharper characterization of the hierarchy problem. In the standard model, you might think, well, the dumbest thing you might think is that the operator H dagger H, clearly that cares about MH squared. If MH squared is negative, it's given by, basically V squared, turns on, it's basically given by MH squared. And if MH squared is positive, it's equal to 0. And that would be true at tree level, but because of quantum mechanical corrections, that's not true. And in fact, in the standard model, we just can't compute the expectation value of H dagger H. That's one way of phrasing, another way of phrasing the hierarchy problem. So for instance, if I attempt to compute it, I would draw the usual loop diagram that we always draw, very closely connected one, and there would be a sort of cutoff squared contribution to it. So we just can't compute this in the standard model. And this is similarly true for almost all local operators. For example, let's look at the expectation value of the Yukawa coupling operator. Well, there it is, put it in there, but we can again close the loop with the Yukawa vertex and we get some quartically divergent thing and we can't compute it, okay? So almost all the local operators in the standard model, we can't actually compute their expectation value. If we say it another way, we can imagine very weakly coupling H dagger H to some field phi, with some coupling epsilon phi H dagger H. But if I write this down, this operator has exactly the same symmetries as this one, where M star is some kind of high energy cutoff. And that would tell us that we just can't calculate. For example, the phi potential, the linear term in phi, we just can't calculate. It's not calculable. We have to take it from experiment. Okay, so that's the so this is a close cousin of the usual hierarchy problem, is that local operators don't actually care about MH squared. Okay, so that's kind of interesting. Two-point functions and higher point functions care, but local operators don't care about MH squared at all. There's actually one interesting counterexample to this, which is the operator trace glue dual. Trace glue dual is naively a total derivative, but it's a total derivative of a gauge invariant operator. This is the famous story of the anomaly. And so because of non-perturbative QCD effects, glue dual is actually non-zero if we have also a non-zero theta angle. I should have actually put a theta here. It goes like lambda QCD cubed times M up. And there's a theta because it violates parity. So we need a theta angle for this. But at least this combination, lambda QCD M up cubed, does sensibly depend on MH squared. So that's interesting. This operator glue dual, you can think of as triggered by the weak scale. In other words, if MH squared is positive, it's basically 0. It's extremely tiny. As MH squared switches sign, it's triggered and it turns on, and it's sort of proportional to how much electroweak symmetry breaking there is. Okay, so this is the notion of a trigger, an operator that sort of turns on, correlated with what's happening with the Higgs mass squared. And this trigger is used cosmologically in the context of relaxion models, for example, to address the hierarchy problem. But there are other triggers. Are there other triggers? In the standard model, no, the only one is trace glue dual. But there are very simple triggers that are possible in 2x doublet model extensions of the standard model. So I'm going to talk about, things that just at a very, very simple limit of a 2x doublet model. So let's say we have two Higgses, H1 and H2, but where H1, H2, this operator H1, H2 is charged under the Peccei-Quinn symmetry. H1 and H2 are taken to have opposite hypercharge in my assignment here. They're charged into some discrete Peccei-Quinn symmetry. And for phenomenological safety, we'll say that H2 couples the fermions and H1 does not. All right, now in this picture, now I can ask, what is the expectation value of H1, H2? Sorry, I called them HUHD here. It should be H1, H2. Well, I can't close this loop because of exactly the Peccei-Quinn symmetry. Okay, because of so I don't have the same issue that I had before. And therefore, the expectation value of H1, H2 is actually calculable. And this is what it is, trivially at tree level. In order for H1, H2 to get a VEV, both H1 and H2 have to get a VEV. And therefore, this operator only gets an expectation value where both Higgs mass squareds are negative. The situation is slightly more interesting because of the breaking of chiral symmetry in QCD, and so there's a detailed correction to this that involves that involves lambda QCD. But this is basically the picture, is that they both have to get a negative mass squared in order for the operator to turn on. Now, of course, this Peccei-Quinn symmetry must be broken, otherwise we'd have a weak scale axion. And the conventional way that people talk about this in 2 exoublet models is to add a B term, a B H1, H2 term. But if you add this B term, it ruins the trigger mechanism. And that's because when I look at this loop, I can now put an insertion of B here. And so this expectation value is of order B, completely independent of the values of M1 squared and M2 squared. So we're basically back to the same situation we're in before, where it doesn't care. This operator does not care about what's happening with the Higgs mass squared. But it's possible to make a trigger-happy 2 Higgs doublet model where we break this Peccei-Quinn symmetry to a Z4 symmetry where with only a quartic term in the potential. So the only thing that breaks the PQ symmetry and gets rid of the weak scale axion is this H1, H2 squared coupling, but crucially, B is equal to 0. In this case, this operator H1, H2 can't be generated by anything, by any loops in the ultraviolet, because the only thing that breaks the PQ symmetry is lambda, and lambda has even charge under this PQ symmetry, while H1, H2 has charge 1. So in this limit of the 2 Higgs doublet model, where crucially the B term is 0, the operator H1, H2 is triggered by the Higgs mass squared, and crucially, we need both of them to be negative to trigger it. Okay, so again, in the context of the potential, we have some general 2 Higgs doublet model potential, but again, the important point is that the only thing that breaks the PQ has charge 2. And this makes this model impossible to decouple. Okay, so there's no limit of this theory where we can take the other Higgses and make them heavy. In a moment, I'm going to tell you what this trigger is good for. The idea is that if you can make an operator sensitive to electroweak symmetry breaking, then we can use it in order to sort of justify why the Higgs mass squared has got to be very tiny. So I'm going to come to such a justification in a moment. But there's a more model independent point, which is there any indication that the weak scale is triggering some local operator in any way? In the standard model, the only thing that could trigger is this operator glue dual. But in this 2 Higgs doublet model, it can trigger the operator H1, H2, but only in this interesting limit where B is equal to 0, crucially. And that makes it impossible to make the other Higgses heavy. The reason is that conventionally, the only way we can make the Higgses is put them anywhere we want by making the B term big. But if the B term is 0, the only access we have to making the other Higgses heavier is to make the quartic couplings in the potential big. And we can't do that. We can't make them too big without sort of hitting Landau poles right at the TeV scale. So, and also crucially, if we want this operator to be triggered, we have to have that both of the Higgs mass squareds are negative. So we're definitely a limit where it's not a 1 Higgs dominated electroweak symmetry breaking. Both Higgses have to be negative. Now, in order to not to just be manifestly dead from the measurements of the Higgs so far, clearly we have to have that the VEV of the second guy over the first guy is less than 0.3 or so. And when you look in detail at what's alive in the parameter space, the second CV even Higgs is always lighter than about 100 GeV. Everyone else is lighter than 200 GeV. So again, crucially tied into the structure of this idea is you cannot decouple anybody. You can't hide it. But it's remarkable that it still seems alive, that there's a, I'd say 15% of the parameter space of this model is not yet dead, which is very surprising to me. And it will be incisively probed with the high Lumi LHC. We're saying we have all these super light guys lying around that we haven't seen, and of course we give huge signals at a Higgs factor. I don't have time to go through this in detail, but this is you can see the sort of detailed discussion of all the collider constraints. We think we covered all of them that are known in the paper, and so there are just some sort of panels here as a function of the CP even Higgs mass for various choices of the charged Higgses, and the ratio of the VEVs, V1 over V. So you see that there are definitely places there's no white area at all. They're totally excluded, but there are regions with decent size parameters, decent chunks of the parameter space that are not yet excluded. And look at the horizontal axis here. Okay, everything is lighter than 80, 90, 100 GeV. Okay, so this is a limit of a 2x doublet model, where the simplest bilinear operator is triggered by electroweak symmetry breaking, and it's alive. It is now alive, but it has a target on its back as far as the high Lumi LHC is concerned. And let me then just close by giving a picture for how you could use this trigger to actually explain the hierarchy problem, or explain the origin of the Higgs mass hierarchy, at least by correlating it with the smallness of the cosmological constant. And just not to go on too long about this, I'll just give you the sort of the cartoon level idea here. So there's a picture that's been talked about a lot, which is that in order to explain the smallness, for example, of the cosmological constant, we can rely on the fact that it's simple to imagine underlying unique theories of the world giving us huge numbers of vacuum. And this is normally talked about in the context of string theory, but you don't need to know any fancy string theory to think about this. Just imagine a theory that has n scalar fields, each with a potential that looks like this, and they have 2 to the n minimum, and they each have 2 minima like this. So if you have n of them, you have 2 to the n minima. That's the sort of crucial point, is that you can have exponentially many minima. So if n is of order, 100 or 200, which is not that crazy, we have order 100 species in the standard model. It's not crazy to imagine there's like hundreds of other scalars in other sectors that we haven't seen yet. Then it's easy to get exponentially large numbers of vacuum. And if that happens, then just accidentally, one of those vacua will have tiny vacuum energy. That's the basic idea. All right, now, of course, you might imagine that if these scalars are out there, they're all very heavy. They're at the gut scale or something. And I want to stress that we could, in principle, a lot of discussion of the possible presence of a huge landscape of vacua is filled with stupid discussions about philosophy and metaphysics, about how they're populated out there in the multiverse. But there's an aspect of this which is totally sharp and totally, in principle, experimentally accessible, which is you could produce these scalars in principle and see that there's 100 of them and see that they have 2 minima each, and sort of confirm that there are indeed 2 to the large number of different metastable vacuums. Okay, so, but in the conventional picture, all these guys are very, very heavy. And what we're going to do is imagine that this sort of heavy part of the landscape that sort of allows us to scan the cosmological constant, maybe the Higgs mass and other quantities, is, however, not that big. So you might need like 10 to the 120 vacua to find one with a small enough cosmological constant, but maybe this sector only has 10 to the 70 vacua, not enough to get one with a small enough cosmological constant. But there's another landscape of very light fields, okay? And there's also many of these guys, but these guys have a potential with a Z2 symmetry. So there would be 2 to the n minima here, but they're all totally degenerate and useless for further scanning the cosmological constant. So you have 10 to the 70 minima here. You also have maybe 2 to the 50 other minima lying around here, 2 to the 100 other minima lying around here, but because their energies are exactly degenerate, they don't help. They don't help scan, to find a vacuum with a small cosmological constant. But we imagine that these light scalars are also coupled to the Higgs or to this trigger operator H1, H2. And therefore, if this operator turns on, if it's triggered, then we can change what this potential looks like. So the idea is that if you turn on, you can slightly tilt this potential. Now, when we tilt it, we will get 2 to the n different minima. So we'll get fine structure in these vacua. And now we will get many, many, many different ones that will allow us to find one with a small enough cosmological constant. But we can't tilt it too much. We can't make the size of this trigger too big, because if we tilt it too much, then we lose 2 minima. We just go back to having 1 minimum. And once again, we can't find a vacuum with a small enough cosmological constant. So only for a range of these trigger values, so this operator H1, H2 has to turn on, but it can't get too small and it can't get too big. And that explains the origin of the hierarchy in this picture. Okay. So that's how we can use this trigger to give an alternate origin of the weak scale, and also correlate it with the cosmological constant. And there are other things you can say about these scalars. There are sort of bounds and signals from them, from long-range forces. They're very, very light scalars. So we can really imagine seeing them in at least in the most optimistic region of parameter space in long-range forces. And also, the electroweak symmetry breaking in the early universe triggers the displacement of these scalars that then sort of coherently oscillate, and the coherent oscillations could give us dark matter. All right, so that's a rationale for what this trigger is good for. But I want to stress again the most crucial point as far as the logic of this meeting is concerned is that this is a picture of the world where a good reason there's a symmetry that is associated with the weak scale of the trigger, and the symmetry forces a 2x doublet model with super light scalars. And amazingly, we have not totally ruled it out at the LHC. Okay, that's the most remarkable thing about the set of ideas to me. And then, as I said, it's a target on its back as far as the high Lumi LHC is concerned. All right, so that's all I wanted to say. Sorry for going on a little over time. I want to stress again that just go back to what I said. The failure of perfect naturalness was not a surprise. The mystery of the weak scale has only become deeper. And there are, I think, decent to good theoretical motivations for new particles around the corner. I've given you some of them. Other theorists who've thought about these things for many years will give you others. But as experimentalists, it's highly motivated to sort of continue and pull out all the stops to get as much as we can out of the data. Thank you.
Thank you, Nima. Very nice talk. To all of you in the audience, Nima will still be around if you have questions. Now I'm giving the floor to the leader of the discussion, the first discussion session of this workshop. Welcome, Vishwarup Mukhopadhyaya. I hope I pronounced that correctly, from the Indian Institute of Science Education and Research in Kolkata. You have the floor in the discussion session. And as I said, if anyone wants to talk to Nima, he's still around for a bit.
Okay. We have just heard a lot of observations, including deep insight on a large, on a very big canvas. Since the leitmotif of this meeting is LHC data, so out of the big canvas, let's start by discussing some points gleaned out of that canvas, as well as some points that came to my mind just now. Okay. So we start by gleaning out a few points that connect to data, and some of the points, which at least a majority of the points I wrote down independently on this page, are actually contained as seeds within the observation made in the previous talk. Now I'm just reading out, and people are afterwards free to discuss, initiate discussions based on these points, on the original statements made in the canvas, as well as anything else that their imagination is triggered by. The first observation that I would like to emphasize on is LHC has seen, if anything, a 125 GeV scalar, and the observations which face us till today are not inconsistent with any message of physics beyond the standard model. In some way, they tickle us towards that on issues starting from naturalness to vacuum stability. So any message that can be extracted from the Higgs data on beyond the standard model in the upcoming run of the LHC, including its high luminosity, is a very pertinent question where people may have a lot to say, both from the angle of model independent interpretation of the data and also in the line of model dependent and specific model situations. The next point, again, whose seed is contained within the previous talk, is the issue of the naturalness of the electroweak symmetry breaking scale. Of course, this is a vexing question, and supersymmetry for once provide not only a guideline to avoid this problem, but also kind of lead us to certain naturalness criteria of various scenarios proposed, whatever their acceptability is. Now, if there are scenarios other than supersymmetry in a general way, developing such naturalness criteria of any candidate model is a rather challenging task, and whether the LHC data can be of any use in treating such criteria, defining such criteria, testing the viability of a scenario in terms of this criteria is, in my view, a very pertinent question. This is especially so because non-supersymmetric solutions to naturalness problems often are suggested in terms of slightly ad hoc scenarios in the way of some effective theories without proper UV completion. And the scale of the effective theory, its stability against radiative correction in turn, is a question that is often started when these models are discussed. Whether LHC data can provide us some new glimpse or open some new doors to such questions is a pertinent point. Then one of the most concrete and persistent things that bother us about the existence of new physics is the observations related to dark matter. Now, coming down to mundane issues, terrestrial issues related to dark matter, starting from direct observations to collider data, dark matter observations, and of course, in view of astrophysical and cosmological observations, dark matter is very likely to lead us to a scenario which should have some special properties. The most important two properties being a Z2-like symmetry, a Z2 symmetry or some similar symmetry, or a sector with long-lived particles. Now, whether clearer hints on any of these fronts may emerge from the yet unseen or yet unavailable LHC data, it is probably $1 million question about the real nature of our existence in the universe, where dark matter has a role to play. And last but not the least, this is again a point contained in the previous talk, is whether effective operators carrying the messages from new physics whose relevant scale is just above the LHC reach, or which contains some UV completion which starts just beyond the LHC reach, whether signatures of such effective operators can be probed with greater vigor in the incoming data. So these, ladies and gentlemen, are just a few points jotted down arbitrarily, but quite remarkably contained in the talk which we have just heard. So people are free. Now the floor is open to discussions on any such points and many more that rightfully be triggered by the discussion that we have heard. Now, let me try to see. I can hear a question from Zinkai Wen. Organizers, are you going to unmute him and let him ask the question? Then we'll go for more. Zinkai Wen.
I can unmute him or her if
yes,
that's what's
it is best if, I don't know if it's he or she, but if she can read out the question or ask it directly, probably it will be more lively affair. What happened? The questioner is not to be noticed. In that case, should I read it out?
So I allowed this person to unmute themselves and speak. If they don't speak up, you can read out the question.
Yes. Yeah. Zinkai, when we request you to unmute, you are unmuted. So can you ask your question directly to the speaker? No. Okay, let me read out the question in that case. Excuse me, Professor Nima Arkanim Hamed. In the paper, the weak scale as a trigger, I understand that you get the trigger, H1, H2 vacuum expectation value, using the methods like the Coleman-Weinberg potential of the scalar phi, but I don't know why you use the trigger to search for vacua for phi for suitable cosmological constant. I think it is something like the anthropic principle, right? And the final part of this paper showing phi as the dark matter candidate, but I just don't understand the necessary connections between these three objects. So I request the speaker to answer the question.
Sure, yeah. So let me first just make a general comment about the anthropic connection, because this is a point which is it's a simple point which is usually conflated in this discussion. All the naturalness difficulties have to do with the idea that if you had just a sort of a single vacuum, you imagine you have just one theory, that that it's unlikely that that the parameters of the theory would be such that seemingly very, very different contributions to either the Higgs mass or the cosmological constant would conspire to give you a number that's much, much smaller than what you'd naively expect from dimensional analysis. And of course, what's remarkable is that, as unusual and strange as that might be, that's what appears to be going on in nature. We don't see it in condensed matter systems, where this idea of naturalness works perfectly and where the whole Wilsonian paradigm came from. But it seems to be the way things are in nature. So nature does not look like a condensed matter system. That's extremely interesting by itself. But the logic of the discussion changes if you have many vacua. And the first thing, and this is the distinction I want to make, the first thing is that if you have a large number of vacua, then it becomes possible to find one of them that has a small cosmological, one or some of them that have a small cosmological constant or a small Higgs mass, without having anything crazy in the actual parameters. You just have sort of garden variety parameters. Like I said, you have these garden variety parameters, you have these n different scalars, 2 to the n minima. But the very fact that there is those exponentially many vacua makes it possible to find one with a small cosmological constant or a small Higgs mass. Then there's a separate question: why do we find ourselves there? But it's already, one step of progress to even make it possible to find one which has the appropriate values. The question of why we find ourselves there could be an anthropic one. Or maybe there are other explanations that we don't know yet. That part is more speculative. It could be that in order to make structure in our universe, a la Weinberg's argument, we need a tiny cosmological constant. Maybe that's a correct argument. Maybe there are sort of deeper motivations why we should find ourselves in that vacuum with the smallest of all the cosmological constants. Who knows? But the non-philosophical part is that it's possible to find one vacuum with a small enough cosmological constant without asking for any strange correlation between the parameters of the theory. So you could, I'm not being disingenuous. You could say that the motivation for the small cosmological constant is anthropic, but what I'm saying is that the most hardcore invariant statement is that it makes it possible to find a vacuum with a small cosmological constant. And so that's the idea in this model, is that there are not enough parameters, that there's not enough vacua in the sort of big, high energy, heavy landscape to scan finely enough for a small cosmological constant, but there are enough to fine-tune the Higgses to be light. And making the Higgses be light then makes it possible, when they trigger this operator, to have access to many more vacua that does make it possible to find a small cosmological constant. So in that way, it gives us sort of a landscape, a motivated explanation for the correlation between the Higgs mass and the cosmological constant.
Okay, thank you, Nima. I don't know if the speaker, if the person who asked the question is satisfied, because we are not hearing the voice of that person. But let us take up the new question. Is there any question? Because the persons who are assisting me have not brought anything to my notice. I can't see anything in the chat box, nor in the Mattermost forum yet. After your talk, I'm just trying to find it out.
I think Tao has a question.
I raised my hand.
Tao, I can't see Tao, your raised hand. Please
Yeah,
ask
so
your
yeah, on the other side, I'm on the panel side. So this is not a question, but a follow-up comment along the line that Nima emphasized for the offshore Higgs studies in respect to the LHC aspect. I think normally when we think about the search for new physics, we usually say one is a precision, the other one is the energy threshold, go to the high energy end. But I want to emphasize that the LHC actually has both. So of course, we'll continue to study the Higgs properties to a higher accuracy. Hopefully we reach a percentage level for most of the important couplings. But LHC has the potential to go to the energy frontier as well. So this is related to the offshore Higgs. And recently we have had 2 papers along this line. So obviously the best channel to begin with would be the Higgs with easy and very nice, easy to reconstruct final states. In particular, it's known that the Higgs signal diagram has a destructive interference with the standard model continuum background. But if so happens that if a TT bar Higgs coupling, which is the most important coupling Nima emphasized, somehow miraculously shut off, it becomes a small 0. And this signal diagram seems to be vanishingly small, but the overall observable signal is enhanced due to the absence of the destructive interference. This is extremely interesting phenomena that you search for this high energy end for the invert mass in the hope to dig out the Higgs signal. But if you have enhanced the rate over the standard model expectation, that means the top quark Yukav coupling is suppressed. So this is very interesting stuff there. And I think the point I want to emphasize is that this is the time for the LHC studies to go beyond the precision and go to the energy frontier, both in terms of the offshore Higgs, far offshore Higgs, and high PT Higgs physics. Thanks.
Thank you, Tao. Any response to this observation? So if I may make an observation, Tao, so what you are saying relates quite closely to Higgs pair production at the LHC, right?
I was not commenting on the Higgs pair. It is very much related, for sure.
Yes.
It is very much related. You can search for the Higgs pair production in the same mechanism from the same type of diagrams as well, and a very similar mechanism. But the simplest one is a single Higgs production to decay to Z pair far off shell Higgs, high invert mass.
Yeah. But the pair production rate also can go up as a result of this reduced top quark coupling, right?
It is also true. It is also true. It's a lot more challenging in terms of observational aspect.
Yeah.
But of course, it's more direct to the triple Higgs coupling. No question about that.
Yeah.
It is a very, very important channel to search for.
Sure.
And we'll be lucky to have observation at the LHC. I think LHC has a only very moderate sensitivity to the triple coupling.
Maybe I can make one more comment that I forgot to make in the talk,
Sure.
and which is probably difficult for the LHC. But actually, I don't remember exactly what the story is here. So one of you guys can tell me. But the really most invariant probe of the Euclidean properties of the Higgs coupling, the off-shell properties of the Higgs coupling, would be the running of the top Yukawa. The running of the top Yukawa, I mean, the entire renormalization group is a purely Euclidean phenomenon, totally 100% Euclidean phenomenon. So if we see the expected running, then that would be another indication of anyway, it would be probing the same physics in that way.
Yeah. So in that regard, the running of Yukawa coupling, the running of the top quark mass may also have some relation with that as well.
Right.
indirectly, but it potentially reach the similar physics. Yeah. So there has been effort to do that, but theoretically it's challenging because you have to define your top quark mass properly, and in connection with your measurements. In the measurements, we usually do this Monte Carlo mass to reconstruct the top quark mass, but theoretically you need to do the full proper calculation and definition of the running mass, and there has been a lot of effort in doing that.
Okay, Rohini seems to have a comment. Rohini, can you unmute yourself, and or rather can somebody unmute Rohini? And Rohini,
No, I can unmute myself.
Yeah, you are a panelist, so you can unmute yourself.
I can unmute myself. No, I just wanted to support or supplement Tao's comment, because I think this in discussion on off-shell measurements is indeed very interesting. But also the point you made, Tao, about large PT, that is that LHC can do, is kind of related, I think, to the last point that on Vishwarup's slide about signatures for effective operators. I mean, as we know, the large PT Higgs and the large PT top regions of the production can really probe. And Nima's talk has given us sort of a picture where there are very deep theoretical ideas which will give rise to these changes in the couplings. But this point about going to large PTs, I think, is very, very important. And that's what a high-lumi LHC can really do. So I wanted to just emphasize the point that Tao was making in half his statement.
Thank you, Rohini. That's very true. In fact, it's interesting to look into the details. And Nima, of course, was arguing about this the Euclidean nature. In fact, the high PT physics, high PT Higgs physics is complementary to the off-shell. It's different. In fact, it's really different. The on-shell Higgs, exactly. So I think Rohini, you made a very important point. This is a really complementary, not even it's high scale. The off-shell Higgs, it's a space-like. Even it's not on-shell, the space-like. Sorry, time-like. So then if you do the high PT Higgs, the momentum transfer, the momentum of the kick to the vertex actually is a space-like. It's a very different physics, very interesting physics, important physics. That's why I want to emphasize that this is the time for our LHC experimental colleagues to pay attention to the rather low event rate in the as high possible, as a high energy, as a high PT region as we can. Thank you, Rohini. That's exactly the important point. We didn't get a chance to discuss details, but it's very rich physics there.
And also in the subsequent sessions, our experimental colleagues may enlighten us by making more comments on this. It's a very important point.
Yeah, and high PT for the Higgs could mean very off-shell tops, as in the TT bar Higgs example, right?
Exactly.
So,
yes.
That's exactly
that's really the point. Yeah.
That's
and
exactly
again,
right.
I really think that's the like super model independent measure of our understanding of the origin of the Higgs mass. That it's kind of amazing that 10 years into the LHC program, we still have such a poor experimental handle on it. So I really think that's something, it's very important.
So exactly, Nima, that's why I said this, that the large PT modification comes from sort of different ideas, and it's really different. I mean, than looking at the only the off-shell effects that Tao was mentioning. So I think we are all on the same page.
Anyway.
I have another rough comment that goes well, that my talk actually the first part was in violation of this comment. But I think it is important for theorists thinking about these things to try to come up with concrete models. That the first part of my talk was not concrete, but at least at least some rough experimental direction of things to look at, which I think many of us appreciate anyway. But there's a real advantage. There's something very good. I mean, it's a very obvious point, but something good happens when you make a precise model, that it forces you, it sharpens the thinking and focuses you into particular places you might not have thought of otherwise. So it's this very simple example of the 2x doublet model with the B term 0. I mean, it's theoretically a trivial thing, but it opens up this kind of area of parameter space of weakly coupled light Higgses that I was sure would have been ruled out already. But when you have a specific idea for what's going on, it leads you to think about things more precisely and exposes more holes than just thinking about them sort of in the abstract. So I think anyway, that's just an encouragement to more of our young model builder friends to try to build very specific models if you can.
Okay. I don't know how much more time the organizers permit us, because we are.
Bishop, there's one question that comes from the MetaMost chat from Andre Patrascu. I hope I pronounced this one correctly. If he wants to speak up, I can unmute him or her, and then we can have the question. Otherwise, we can move on. So let me quickly check that.
It was a question that was asked in advance of the meeting, right?
Yeah.
So if he asks the question himself, it will probably be more helpful.
Okay, I cannot.
Okay, I can read it out then. Nima's observation on the cancellation between the log terms and the other terms is interesting. It has a nice mathematical interpretation, but I noticed something similar with a link between planar and non-planar diagrams following Etof's approach. Any comment, Nima?
Sorry, I didn't hear. You said that you noticed something similar in the link between planar and non-planar, or are there similar? Sorry, I just didn't hear what the statement was.
Yeah, this is what precisely the question or comment says. I'm reading it out once more. Okay. Nima's observation on the cancellation between the log terms and other terms is interesting. It has a nice mathematical interpretation, but I noticed something similar with a link between planar and non-planar diagrams following Etof's approach.
Yeah, I don't know. I haven't seen that, but I would not be shocked, because once you see this, once you're sensitive to this phenomenon, you actually see it all over the place. It really explains many of these little accidents that you sometimes see in explicit calculations. And I should mention that the sort of mathematical fact here has been known since the 1800s, and since the mid 1800s. And when mathematicians try to prove that a number is irrational, they actually do it like this. They often find some way of approximating it to extremely good accuracy with a rational number, and that, ironically, is the way to prove that numbers are irrational. So this is not it's not a totally random fact. It's a relatively sort of deep thing in the structure of number theory, and it's come up a number of times in the 1800s. And actually, my toy example about the logarithm, more sophisticated examples of that sort go back to the late 1970s with celebrated proofs that numbers like the zeta function of 3, the zeta value at 3 is irrational. There's a celebrated proof of that fact that's a version of the cancellation for log 2, a more fancy version of that cancellation for log 2 that I told you. So this is not some random weirdo phenomenon. It's a relatively interesting structural phenomenon, and it does show up all over the place. And as I said, once you're sensitive to it, you see it all over the place. So if you've seen it elsewhere, that's great. I'd be very curious to see the context, but I would not be surprised, because it does show up in a lot of places.
Thank you, Nima. More questions or observations, or are we nearing the end of our time limit?
Yes, Bisharuk, thank you very much. So our last comment also, there comes with a few links in the discussion forum, so I want to revert any further discussion to that one. And let's continue with our program with Bhupal Dev's next talk. I mean, the next talk from Bhupal Dev on anomalies. Bhupal comes from the Washington University in St. Louis, and let's see if he's online. I see he's online.
Yeah, I need to unshare the screen now. Thank you.
Hi, Oliver, can you hear me?
I can hear you, yes.
Okay. Yes.
So
we can also see you. Yeah.
Okay, great.
See you and hear you.
Screen. Okay. I hope you can see my screen.
Yes, we can also see your screen.
Okay, great. So can I start?
Anytime you're ready.
Seem to make it full screen for some reason. Okay, good. Okay, so I would like to thank Oliver and Bruce and the other members of the organizing committee for giving me this opportunity. I was asked to give an overview of anomalies. So just to make things clear at the outset, since there might be people from diverse backgrounds here. So here by anomalies, we mean the experimental results that conflict with the standard model, but fail to overturn it for lack of sufficient evidence. And we can say that this is an era of anomalies. There are a growing list of such anomalies, such anomalous data that we are seeing now. So most of them could be very well be due to some statistical fluctuations in the data, or could be systematic uncertainties, or some theoretical issues that has not been understood, or some experimental error simply. But there may be also the possibility that some of these could lead us to the path, to the right path toward new physics. So I would take these anomalies as a good driver of scientific creativity. For theorists, it gives us some challenge to grapple with the data and find models that fit the data naturally without too much finagling. And from the experimental point of view, also it gives a challenge, a fresh challenge to the experimentalists to better understand their instrument, better understand their systematics, and reduce the background and so on and so forth. So you can take it in a constructive way. Let me just start with advertising something that we have been doing over the last 2 years. This is the Anomalies series of workshops. They started as some informal discussion with Priyatos from IIT Hyderabad, and we're trying to write a grant for the Indo-US forum, and we thought of this topic as a suitable topic for discussion. And so we started in 2019, and I couldn't be there personally, but I heard that it was successful. And then we thought of doing it again in last year. Unfortunately, that was online because of the current situation, and we hope to do it again in this year. Most likely it will be in July or August. And I invite all of you to attend. So we may not be able to send personal emails to all the participants here, but you're encouraged to attend this meeting. So our goal is to really establish this as kind of a mainstream annual workshop series, like for example, the series SUSY series, or things like that. And we of course need community support to have this. So why I said we need community support? Well, because still anomalies are kind of mostly regarded with skepticism in the bigger community. And in some sense that's justified, because doing like chasing anomalies, it's like sometimes it's dubbed as ambulance chasing. So is it really worth it? Well, it certainly does lack the grandeur of trying to solve big problems like naturalness, hierarchy problem, or quantum gravity, stuff like that. But still, this has its own benefits. Also, the other criticism that anomaly chasers get is that just about every anomaly in the past decades has disappeared over time. So, and then whatever you are trying to play with, that will also disappear. So why waste of time? It is certainly true, but also perhaps there will be some anomaly which might eventually turn out to be true, and that could then define even the next decades of our research field, and it could even turn out to textbook material. So it's certainly worthwhile hunting down these small blips in the data if you have nothing else better to do. And it offers, as I said, fresh challenges to both theorists and experimentalists, and it inspires new analysis methods and tools. And we have several examples of that. So in this context, I should emphasize here, one of the main themes of this workshop is open access data. So this is very crucial in resolving the anomalies. So more open access data and more collaborations between theory and experiment, these would play a crucial role in resolving these issues. Okay, so let me start with making some observations from the past. Those of you who have been around for more years than me, you would know, of course, many more such stories. But I'll just take some recent examples. The first one I take here is the opera experiment. I guess most of you know about this infamous result that they have superluminal neutrinos, and they even had an overall significance of 6 sigma. Okay? And over 100 papers were written about that. But it just turns out that it was simply an experimental error, some loose cable, and then eventually they came to agree that their neutrinos are not superluminal, rather they're consistent with their speed is consistent with the speed of light. So this is just an example that that errors do happen, experimental errors, and then and that's normal. So even if an anomaly has a significance of more than 5 sigma, that still does not really mean that that might be true. So it could turn otherwise. Now let's take another example. This most of you will be familiar with. This is the 750 GeV diphoton excess. So in late 2015, I believe, there is this excess in the diphoton channel in both Atlas and CMS, and the significance was actually quite high, roughly around 4 sigma level. But it just turns out, and there are more than 500 papers written on this. But it just turns out that it was just a statistical fluctuation. So as soon as they collected more data the next year, then the significance of this excess just decreased from 3.9 sigma to 2.3 in Atlas and 3.4 to 1.9 in CMS. And now, if you look at the latest data, then it's not even there. Okay? So don't even talk about it after ICEP 2016. So this is another example that yes, fluctuations are there. Statistical fluctuations can happen, and they do happen most often. So that's part of life. And then the next one I would like to point out is this Koto anomaly. So this maybe some of you may not be familiar with what Koto is. So let me just explain the experiment a little bit here. So this is an experiment at J Park. They are looking for the K-long decays to neutral pions and a neutrino pair. Okay, so this can happen in the standard model, but that is this is a flavor-changing neutral current. So this is highly suppressed, and you can calculate this penguin diagram and find out what's the branching ratio in the standard model. That's 3 times 10⁻⁻11. So the theory uncertainty here is very small, like roughly 2%. So this is a very good probe for new physics search, and that's precisely the reason why they're looking for this rare decay mode of K-long. And in 2019, they did find some anomalous result. So this is their signal region. I hope you can see my cursor here. So this dashed box here is the signal region, and there they expected like 0.05 plus minus 0.02 backgrounds, and they got 4 signal events. So this is a quite statistically significant result. So out of these 4, one of the events they later identified as some veto issue. So you can reject that, but still you have 3 signal events. Well, you have 3 events compared to 0.05 background. So that's a quite significant result. But that led to some questions, of course, that how can we really understand this signal? There is a famous bound known as the Grossman-Neer bound that connects the branching ratio of the K-long to neutral pions to the charged K-on to charged pion branching ratio. And in particular, the neutral K-on, the K-long branching ratio cannot be larger than 4.3 times the branching ratio of the charged K-on. And this is a pretty generic result, and this holds true even if you have some BSM physics, not just some standard model physics. This just comes from isospin. So if you have this excess in the K-long to neutral pion, then you would also expect an excess in the K plus. But this channel has been searched for in the past, and in particular, NA62 has put a very stringent bound on this K plus that was at the level of 10⁻⁻10 at this time. And so if they don't see an excess there, then how can we see this excess in the K-long? So people thought of different new physics scenarios here. And one of the particularly interesting ones is to consider a light scalar. So what happens here is that if you consider just a generic scalar, singlet scalar mixes with the Higgs boson, and then the Higgs, of course, couples to the standard model quarks. So through this, you can couple this light scalar to the quark line, And then this scalar, if the mixing is small, then this will be long-lived. And then instead of having this k long to pi naught nu bar, you have k long to pi naught plus this phi, this light scalar. And this phi goes unnoticed. So instead of this 3-body decay here, you have a 2-body decay, but since the this phi is unnoticed, you cannot distinguish it from the neutrino pair. So then you basically have this signal here. You can have this signal, and this has been studied by many people here. I just take this plot from this paper, and what it shows is that we have this mass versus the mixing of the Higgs plane. And here, this blue region is this Koto that can explain this Koto excess, and this seems there's some region which is consistent with all the experimental constraints, including this NA62 bound that I mentioned. So so this is consistent with this Grossman bound. Okay, so this is one way to avoid or to avoid partly the Grossman bound. But so this is all good, but it just turns out that in the updated version of their results from Koto, they claimed that they had before underestimated the background. So here is the new plot here, and from the again from this same region of this the signal region here, now you have the same 3 events, but now you have 1.22 background plus minus 0.26. So if you calculate the sigma, then it turns out that the probability of observing 3 events is like 13%. So this is really small. So now this is simply disappeared because they had underestimated the background. So this is another lesson. So the first example we had seen, there was an experimental error. The second one is just a statistical fluctuation in the 750, and then here is just underestimation of the background. So these are some of the issues that we have to be aware of when you're thinking about the anomalies. But nevertheless, there is also some success story that we have from the anomalies, and I'd like to point out this famous example, and this has been already mentioned several times in the last talk and in the discussion session, but also so I'd like to just emphasize again that the Higgs discovery started with just like an anomalous feature in the data. Okay, so of course we know that expected Higgs to be there, but it didn't know where it was, and this the signal started out with just like a small 2.8 sigma excess in the Higgs to gamma gamma and a 2.1 sigma in the Higgs to ZZ, and this is from Atlas and CMS at similar results. And then just over time it just grew, and then just within like 1 year. So from 7 TeV when they went to the 8 TeV, combined with the 8 TeV, they just grew to 4.5 sigma in the gamma gamma and 3.6 sigma in the CMS. And when you combine these two, then it was over 5 sigma, and then they claimed the discovery. Okay, so this we have to remember that sometimes the signals, it just starts out with a like small anomalous feature that grows over time. Okay, so this just the same result from the CMS. Okay, so what we learned from this story. So of course, once we see the signal, then one has to understand all the features of the signal, and people have just done that with the Higgs. Now this has been beaten to death. People have looked at all the different possible channels, and here is the summary from the Atlas, and then here is the summary from the CMS. So you basically look at all the production modes, and you look at all the decay modes, and then you compare with the standard model prediction. And so everything seems now consistent with the standard model expectations. So you may call it fortunate or unfortunate, depending on your viewpoint. But yeah, so everything seems rather normal here. Okay, but then you could ask the next question. Okay, so how can I use this to constrain VSM physics? There's this nice framework called the Kappa framework. So this is an effective way to study the modification of the Higgs couplings related to VSM physics. So it can so any new coupling that you have, it can modify either the production channel or the decay mode, including even the total decay width of the Higgs. So we can parameterize using these different Kappa parameters, and then using the precision data from the LHC, you can constrain these Kappa parameters. And this is the latest plot from both Atlas and CMS, and so they have nice constraints on all these Kappa parameters. Now, again, it seems consistent with the standard model. Okay, but this is a good way to constrain a large class of VSM models without going into the details of the models. So we can take inspiration from this. This is a new technique, of course, this Kappa framework, and we can take some inspiration from this and devise similar techniques for studying these other anomalies. Instead of trying to fit our own favorite model to a particular anomaly, you can try to kind of devise a way so that you can at once tackle like a broad class of BSM scenarios rather than just fitting a single model. So this is something that I would like to emphasize here. Okay, since we're asked to talk about, give an overview of the different anomalies, so I try to collect all the existing anomalies that are in the literature at the moment. Again, so I'm not a seasoned anomaly chaser, so I might have missed some of these. So please, if you notice any anomalies that is not in this list, then please let me know. And I would like to add it here. And I think the plan is to write a white paper at some point. So I hope people might find this kind of table useful in the future. So here I listed several anomalies, and I have color coded them based on from where they're coming from. So this red is coming from the LHC. So there are some multi-lepton anomalies at the LHC. I'll talk about that in a moment. And the significance, of course, is it depends on how you do the analysis, but for individual channels, it's roughly 2 to 5 sigma, and depending on the channel, of course. And when you combine all of them, it seems to be quite significant. And then there are a bunch of these anomalies in the flavor sector, which are color coded here in orange. And these will be talked about in more details in the next talk by Andrea Scribelin. So I'll just briefly mention this and its connection to the LHC, like the high PT searches in the LHC. So here we have these the rare BDK anomalies, the semi-electronic BDKs, both in the charge current and neutral current. And that has been seen in 3 different experiments like Babar, Bell, and LHCb. So again, so this just cannot be dismissed as just some statistical, some systematic effect. It has to be something deeper than that. And then we have this long-standing muon G-2 anomaly. So the Brookhaven experiment has measured this the G-2 of the muon, and they found this agreement with the standard model. So over the last 15 to 20 years, people have tried to improve the standard model prediction for this, and now there's been incredibly precise. People have also done a lot of lattice simulations, and from there, still seems like the significance of this discrepancy is about at 3.7 sigma level. So this could be resolved in the near future because Fermilab is going to announce the results of their muon G-2 experiment very soon. So it was supposed to be announced last summer, but because of COVID, it was delayed. So hopefully this year, sometime soon, we'll hear about it. So this could be resolved soon. And then there are these other anomalies in the CKM sector. There's a CKM universality problem. Well, the CKM unitarity problem. So the Kabib angle I think there's some anomaly of the 3 sigma there. And then there's also some lepton universality in the tau case, and there is again something like 2 sigma anomalies. And then moving on to the neutrino sector, we have again bunch of anomalies there. So there's this long-standing LSND anomaly, which looked at this nu bar to nu e bar disappearance. The appearance, and then they found I think a 3.8 sigma anomaly, which can in principle be explained by light sterile neutrino. And then Miniboon recently has checked this LSN result, and using a different baseline, different energy, and so on. But still, they also see some similar excess. And combining LSND and Miniboon, now they have like 6 sigma excess. So this is quite significant now. And then there are also a bunch of smaller anomalies in the neutrino sector. One of them it just was announced last year in the neutrino 2020. That if you look at the 2 long baseline experiments currently running NOVA and T2K, then their results do not seem to agree with each other, and there seems to be some 2 sigma tension between the two different results. So this is something to keep an eye on, just in case it grows in the future. And then in the high energy neutrino sector, there's also an anomaly in the IceCube data. So they look at 2 types of data sets. One is the high energy starting event, or the HESI. where the interaction of the neutrinos with the matter happens inside the fiducial volume of the detector. And the other one is the through-going muon, where you have a new muon which goes through, which produces a muon that goes through the detector. It's produced in the rock outside and goes to the detector. So they look at the spectrum of these incoming neutrinos in these two different channels, and there seems to be some discrepancy in the power loss spectrum that is derived from these two different samples. And then this seems like an 2 sigma. There's also a small bump in the LHC sample around 100 TeV, and some people have tried to fit it with a decaying heavy dark matter. So this is something that might be interesting in the future. And then they're even going to even higher energies, like EEV energies. There is another anomaly that is in this ANITA experiment, a balloon-borne experiment over the Antarctica, where they look for these very high energy neutrinos being produced from cosmic ray interactions with ice and or the atmosphere, and they also seem to find some outgoing events in the EEV range, which is impossible in the standard model, because if you look at the mean free path of the neutrinos in the standard model through the Earth at EEV energy, it's roughly like 300 kilometers. But just the size of the Earth is much bigger than 300 kilometers. So how come these neutrinos, which are steeply outgoing, can come from below? So this is again a puzzle. And then moving on to the nuclear physics side, there seems to be a couple of interesting anomalies there. One is this neutron lifetime problem. So the neutron lifetime has been measured in 2 different ways. One is the beam method, and the bottle method, the trap method. And there seems to be some discrepancy at the level of 4.4 sigma between these 2 different measurements. And one of them agrees with the standard model prediction, the other one does not. So this seems to be a puzzle. But this might have to do with some deep nuclear physics, which of course I don't understand. Then there is another anomaly in this beryllium-8 transition in the atomic experiment. And initially they claimed to have like something like 5 sigmas, and now they have updated the result last in 2019, and now this anomaly has grown to like 7 sigma. So this is something that might eventually be interesting. Although there is a recent paper that claims that this anomaly is completely good. This just came out last week, so I didn't have time to really go through that paper to see what exactly is the issue there. Okay, so now going to the astrophysics side, there seems to be again a bunch of anomalies in the astro sector. So here in the ones in blue, they are related to some dark matter interpretation. So as we all know, there is this ongoing this Gamma Libra anomaly that has now grown to like something like 13 sigma. Can't believe it. So of course they're saying something. There's the annual modulation signal, but whether it's due to dark matter or not, that's still debatable. And none of the other direct detection experiments have seen this. So obviously people are skeptical, but this needs to be understood. Okay, and then for the indirect detection, there is also this galactic center excess from Fermi, and this is again at around 2 to 3 sigma level, depending on which channel you're looking at. And then there is this antiproton or the antiproton and also the positron excess anomaly at the AMS. This is previously there in Pamela, and now it's confirmed by AMS, even moving to higher energies. So this is again at in between 3 to 5 sigma. And then very recently there was this xenon wanton excess that came out. This is in the electron recoil search. So they saw some excess recoil events, which could be attributed to dark matter or some actions in the KeV range. Okay. And then there is this again X-ray line in the at 3.5 keV. That's from the XMM Newton and from Chandra satellites, and this is again at the 4 sigma level. So very recently I also came to know about this 511 keV gamma ray line. So maybe those who are more knowledgeable, they have known this much before. So now the significance seems to be like 58 sigma. I've never seen such a large significance in any of these anomalies. But this is something happening at the galactic center, which is a really messy place. So nobody really understands what's going on there. This could take a while to be resolved. And then also recently there was this Aegis anomaly in the 21 centimeter hydrogen line. So this is at around 4 sigma. Similarly, in the cosmology side, there have been several anomalies. So one of them is this the primordial lithium-7 problem. That so the prediction from the BBN does not really agree with the observation for lithium-7. And then there is this Hubble tension problem. The value of Hubble constant people get from Planck is not same as what is observed from the supernova data. Sorry, no, not from supernova, from the dark energy data. And then from the similarly, there is another recent one in the nanograv experiment that is looking for gravitational waves in the nanohertz range, and they have detected a stochastic gravitational wave background, and they claim very significant excess there, which cannot be accounted for in the standard lambda CDM. And finally, there is this very weird phenomenon of fast radio bursts, very serious radio signals, so which are of millisecond duration, and there is coming repeatedly. Some of them are non-repeaters, some of them are repeaters that are coming from far away, which we do not know about. So this is just a partial list of the existing anomalies. So in this context, what I would like to propose is that we should probably create or maintain an online repository of all these anomalies. So somebody should keep an eye on the literature, and then have up-to-date information on these anomalies. And I hope that maybe the experimentalists can also directly link the results to this website, something like that. That would be really useful, rather than somebody just sifting through all the literature for weeks. Okay, so in the remaining of my time, I would like to focus on few of these anomalies that I listed in the previous slide. First of all, because of lack of time, and second, because this is a conference on LHC, so I'll just focus on those which have some implications for LHC physics. So the first thing I would like to focus on here is this LHC multi-lepton anomalies, and then the other one I would like to talk a little bit about is the B anomalies. Again, we'll hear more about the B anomalies in the next talk, but I'll just focus only on the complementarity aspects in the high PT searches, and then I'll also give a particular example in terms of R-parity volatility SUSY. Then I'll talk about a little bit about the mu G-2 anomaly, and again how to test this at the LHC and future colliders in a complementary way. I'll also give an example of the electrophilic scalar. And finally, if I have time, then I'll focus on the LSND and minimal nexus. Okay, let's see how far we go. Okay, to start with, Bruce, our organizer, and the company have pointed out over the last few years that there are some discrepancies in the multi-lepton final states with respect to the current Monte Carlos. And these appear in different corners of the phase space, so which are dominated by different standard model processes, which are listed here. So depending on which final state you're looking at, the dominant standard model process here could be different. It could be TT bar, W top, or WW or ZZ, or ZW or TTW, and so on. And so this is hard to explain with just simple Monte Carlo mismodeling of a particular process, because these are happening in different processes. Okay, and so they have actually compiled this list of all these different data sets. I mean, they have taken these different data sets and then different final states here and analyze this in the context of this this multi-lepton signal, and so what they find is that there is a significant discrepancy which can be accounted for in a simple BSM model. So where you take a heavy scalar and that decays to a light scalar and the standard model like X. And in that case, just with this, you can have like just a single parameter, it's called the beta G, which characterizes the coupling of this heavy Higgs with the TT bar. You can parameterize how much is your discrepancy in this multi-lepton final states. And here's the plot, and it shows that in the individual channels, the significance is like 2 to 5 sigma, and then when you combine all of them, it goes to like 8 sigma significance. So this is something that sounds very interesting, and this certainly needs to be looked at. So this strengthens the need for the precision Higgs measurements in the future. For instance, you can look at the distortion of the Higgs PT or the rapidity, and then maybe one can learn more about these anomalies. And very recently, they also came up with another interesting observation that now if you have a dark matter which couples to this scalar S, then you can also fit these other astrophysical anomalies that I was mentioning about, in particular the antiproton, the positron excess, and also this forming galactic center excess. So of course there doesn't seem to be a common overlap between these three, but you have to remember that there are some astrophysical issues that one has to be aware of, and just the fact that they are close to each other, the Westport regions are close to each other, that already is a very interesting thing to me. And this is another nice example of the LHC astrophysics complementarity that's often overlooked community. Okay, so if you have more questions on this, then I will let Bruce explain that to you, because he's there in the audience. So instead of me talking about his paper, then he can explain if you have more questions on this. So now let me move on to the flavor anomaly side. Again, as I mentioned earlier, so there is this these different anomalies in the semi-electronic B decays. In the charge current sector, you have B2 C tau nu. In particular, they look at B2 D tau nu versus B2 D L nu, where L could be electron or muon. You take the ratio of that, and that has like the 3.3 sigma anomaly. If you combine the Bell, LHCb, and Babar data. And on the right side, I have here the plot for the neutral current sector. So B2 S mu mu versus B2 S EE. Take the ratio, that's RK, and that has also again like something like 3.4 sigma anomaly coming from Bell and LHCb. Okay. Yeah, I'm not going to discuss all the details of this because this will be discussed in details in Andrea's talk. But what I would like to emphasize here is that there is a nice complementary way that the high PT LHC experiments can really test this. Okay, so what's happening here? So you have this at the low energy scale around the B meson mass. So you have this decays B2 C tau nu or B2 S mu mu. So whatever process is responsible for this, whatever if this is due to some new physics, then whatever new physics operator that contributes to this will also contribute to a process which is listed here. Like, so you can have, in the high PT search, you can have PP2 dielectron or PP2 tau tau. Okay, by L here I mean electron muon. You can have PP2 tau tau, or you can have PP2 tau nu. So these also the same operator will lead to this kind of processes also. So this gives us an independent way to test these B anomalies in these high PT experiments at Atlas and CMS. So this is something that's very interesting. Let me just discuss a little bit more about it. So if you have, for example, this B2S mu mu operator in the standard model, this comes from this penguin, whereas in the new physics sector, it could come from any new physics, but no matter what new physics it is, it will give you this PP2 L plus L minus signature. Okay. And of course, this effective theory here is valid only if the mass scale of this mediator is much higher than the center mass energy. If it is not, then you can still have some simplified models, and you can still look for this dielectron signature. And similarly, for the charge current sector, B2C tau nu, again in the standard model, this is a tree-level process which is suppressed by VCB. Whereas in the new physics sector, you can have again this kind of operator, generic operator that could give contribution to this to the charge current BDK, and also give contribution to signals like PP2 tau nu inclusive. Also, because of SU2 invariance and the flavor structure in the standard model, the BC2 tau nu operator will also lead you to like a TB2 tau nu or BB2 tau tau or BB2 tau tau operators. And the point here is that for BC2 tau nu, this is suppressed by VCB, but in the other operators, they're order 1 effect. So this is, and they're enhanced by 1 over VCB. So this will give you a large signal in the PP2 tau tau in principle. Okay. So again, so as I said, so effective theory that I mentioned here is valid only if the center mass energy is smaller than the mediator mass, but otherwise you can go to simplified models, open up this operator structure, and you can still look for this kind of signatures. And typical examples are like a neutral heavy Z prime, or you can have a leptoquark, which will give you this kind of signatures. Okay, so since I mentioned leptoquarks, let me tell a little bit more about that. So it turns out that this is one of the most favorite explanations of these B anomalies. It turns out that a single leptoquark cannot explain both RK and RD if it is a scalar leptoquark. But if it's a vector leptoquark, this U1 leptoquark, it can explain. From the UV completion point of view, the vector leptoquark was more tricky. We cannot just add a vector particle without doing a full UV completion. But for the scalar leptoquarks, the model building part is a little bit easier. But it turns out that you cannot just have one of them explain both the anomalies. So you need two of them. But in any case, there are strong constraints from these high-PT searches that I mentioned in the last slide on any of these leptoquark scenarios. In particular, there are two different ways you can look for these leptoquarks. You can have just the pair production because they're colored particles. You can just do the gluon fusion and pair produce them and look for their decay. So this will be independent of the Kawa couplings of the leptoquarks because it just depends on the branching fraction. And here is a plot which shows the limit on the leptoquark mass as a function of this branching ratio. So if the branching ratio is 1, of course, the limits will be stronger. Or the branching is less for a particular channel, then the limits will be weaker. So it turns out that these modes like the lepton plus like 2 leptons or the lepton plus jet, the lepton plus jet modes for the leptoquark decay. So they give the most stringent constraints, particularly the electron and muon channels. If you have taus in the final state, then the limits are a little bit weaker. Okay, but still there are roughly around 500 GeV to like 800 GeV level. But more importantly, if you have a larger Ikawa coupling, then you can also have this indirect process where you have the leptoquark mediated in the T channel, but you have this dilepton final state. And since both Atlas and CMS have looked for this dilepton final state, and they have given and they're given all the cross-section limits, you can just recast those in terms of limit on the mass versus coupling, the Kawa coupling in the leptoquark plane. And this is the plot here, which gives this mass versus coupling for different flavor final states, depending on whether it couples to first generation or second generation quarks, and also whether it goes to the first, second, or the third generation leptons. Okay. And again, it turns out that all these limits are pretty strong now. So you cannot have any Ikawa coupling of order 1, for instance, if you want to have like a TeV scale leptoquark. So this puts a very strong constraint on the allowed parameter space that is available to explain the B anomalies. In particular, for the RD star, the charge current anomaly, we need to have a little bit lighter leptoquark, around TeV scale, and this is precisely where these dilepton bounds come into play there. These non-resonant dilepton searches, they have really restricted the parameter space, and now it's kind of shrunk to a very small part of the parameter space where you can explain you can explain the RD star. For the neutral current, it's not that difficult. You can still have a little bit heavier leptoquark, like 2 TeV or 2.5 TeV can still explain. But for charge current, you need to have a lighter one, and that's where this dilepton bounds come into picture. So this turns out to be quite significant. Okay, so I don't know how much time I'm left with, but let me just briefly discuss about one particular implementation of this leptoquark idea. So leptoquark is a generic idea, but there is one nice framework that we all know of, that's supersymmetry. And so you can also have these leptoquark interactions in supersymmetry if you have R parity violation. So now you can have these two different kinds of RPV operators. You can have the LQD type, or you can have the LLE type. So the LQD type will give you this RD star, the charge current anomalies, and combination of the LQD and LLE can give you this the neutral current sector, RK and RK star. Now for this neutral current side, you can have both a tree level and a loop level. It turns out that the tree level, it gives the contribution to the wrong chirality. It gives the right-handed B to right-handed S. Which is not favored by the data. So you have to somehow suppress the tree level and go to the loop level to get the right chirality, the BL to SL structure. But But within this framework, in principle, you can fit both the RD and RK anomalies. Okay. So I'll give you an example with a particular framework which is called the RPV3 framework. That it's RPV SUSY with light third generation fermions, and this is motivated by the Higgs naturalness argument that you need to cancel the Higgs to top loop with Higgs to stop loop. So you can imagine that just the third generation fermions are lighter, and the first two generations can be decoupled. And in that case, you have less number of parameters to play with, and then you can try what that gives for the B anomalies. So here is a summary plot of all this exercise. So here, all these different shaded regions, most of them, they're the exclusion regions, except for this for the RD and RK, which are the 2 sigma and 3 sigma allowed regions. And as you can see, there is a small overlap region here, which is satisfying all the different experimental constraints. So there are a bunch of them coming from the low energy data. The most stringent one is B2K nu bar, and also this D naught to mu plus mu minus and so on. But still, there is some range which satisfies this. And also, it's interesting that the same RPV SUSY interactions also can explain the mu on G minus 2, and that is shown here, that the whole parameter space is allowed by the mu on G minus 2. And also, there is another interesting thing that I mentioned earlier about the Anita high energy neutrinos that can also be accommodated in this framework if you have a light Abino light neutralino around 2 GeV scale. So this all seems to be consistent, and there is still some parameter space that can be probed. Moreover, we can also make some predictions for the future, like how we can test this particular hypothesis. So there are a bunch of this flavor violating decay modes with both the tau decays and then the B decays, which you can look for, and you have this you have definite prediction for this for this overlap region, which in principle can be tested in the future with BEL2, for instance. And just to again mention about this high PT tests, you can also use this crossing symmetry, and this B2C tau nu will definitely give you things like gluon charm going to be tau nu. So this will give you PP to be tau nu at the LHC. And then similarly, B2S SLL can also give you like a PP to BLL. Okay. And the good thing about this PP to BLL is that you can reconstruct one of these BLs, and that will give you a peak at this at the squark mass. Okay, so that is one way you can actually look for this this RPV interpretation of the B anomalies at the LHC. And there are even more processes that you can look at the LHC. So you can, for example, look at all three, like you can look at tau final states. Okay, and these are some of these final states. I think they're pretty difficult to look at, but maybe with a high luminosity phase, you can try to one can try to look for those channels. You can have like top mu plus mu minus kind of final states. And so here is a plot which showed. I'm sorry, this is a very small plot. Able to read all of that, but the interesting region is here. This is the region which satisfies RD and RD star, and these different lines, the red, green, and the blue lines, there are for different colliders like 14 TeV, 27 TeV, and 100 TeV colliders. So even in just the high luminosity phase, you can probe most of the parameter space for this RD and RK in this framework using the third generation fermion final states. Okay. Sorry, so how much time do I have?
So after we started 5 minutes late, and that time is basically over, but you can have 5 to 10 minutes more if that helps.
Okay, thanks. Yeah, I'll just 5 minutes.
Okay.
Okay, great. Yeah, so the next anomaly I would like to talk about is this is the mu on G minus 2. So again, so this is a plot, a summary plot taken from this talk at FINO 2020. So these are the theory predictions, and this is the current experimental result at the BNL. So they are 3.7 sigma different from each other. And the goal in the next Fermilab experiment is to move this is to have more accurate prediction, more accurate measurement of this, so that if this is there, then this will be discovered at 7 sigma significance. So this is something that's going to resolve hopefully very soon. Yeah, so there's a recent development in a related sector. So I think 2-3 years ago, there is a similar anomaly also reported in the electron sector for the electron G minus 2. This is coming from the comparison with the standard model prediction versus the measurement of the fine structure constant in using cesium atoms. And there they found some discrepancy with the experimental result versus the standard model, and that turns out to be something like 2.4 sigma significant. But the important thing here is that the sign is negative, so this goes in the opposite direction to the mu G minus 2. So for mu G minus 2, so if you're trying to explain both electron and mu G minus 2 using a single model, then you have more challenge because one of them goes in the positive direction, one of them is going in the negative direction. So this led to some model building complications. But now it seems like just very recently, last I think a few months ago, there is a new measurement of the fine structure constant using rubidium, and there the discrepancy with the standard model seems to be reduced like just 1.6 sigma, and moreover this is in the positive direction. So now both the electron and muon G minus 2, they are in the like the discrepancy is in the same sign. But this leads to another question that the discrepancy between the cesium measurement and the rubidium measurement of the fine structure constant, they disagree now by more than 5 sigma. So this is something that that I guess this is not related to some new physics. This has to do with some experimental things which hopefully will be resolved soon. So I would not focus on the electron G minus 2. I'll just focus on the muon G minus 2, which seems to be more robust than the electron G minus 2. Okay, so since we mentioned about lepton quarks, which can explain the B anomalies, so we can also see whether they can explain the muon G minus 2. And it turns out that there is a very interesting chiral enhancement effect from the lepton quark loops that gives you a large contribution to the muon G minus 2. In particular, if you have a top quark here, and this is a particular example of the lepton quark with the R2 lepton quark. But yeah, so if you have this, if you have a top quark in the loop, then you have this M2 over ML. So this is the M top over M mu enhancement that you have, and that can explain the muon G minus 2. But something more interesting happens here. So the same couplings that are responsible to explain the muon G minus 2 will also lead you to an additional decay mode of Higgs to dielectrons. Okay, so the same couplings here will be responsible for the Higgs to dielectron. And then if the Higgs also has this this quark coupling with the scalar leptoquark, then you have an additional mode as well. Okay. So you can calculate this, and of course the rate depends on the quark couplings. But you can find out which is the parameter space where you can explain the muon G minus 2, and then look for some correlation in the Higgs to mu mu or in the Higgs to tau sector. And it turns out that that you do have a significant deviation that can be tested in the near future, either with the high luminosity phase or with a future collider like ILC. And if you have something like FCC, hadron-hadron collider, that can even probe it to a high degree. So this is something that's I think very interesting, because this is a way that you can probe the leptoquark solution to the muon G minus 2 using precision Higgs data at both LHC and future colliders. Okay. So the other interesting thing you can do also with muon G minus 2 is that if you think of something like just a purely leptophilic scalar, it does not have any couplings, at least 3-level couplings to the standard model quarks, just couples to the leptons, and in particular to the muon. So in that case, again, the future colliders will play an important role, because they can probe almost the whole available parameter space that can explain the muon G minus 2. So I'm just rushing through it because I don't have much time. But there's another interesting thing that you can do if you have, for example, a muon collider, and then there's a kind of no lose theorem that was proposed in this paper that you are guaranteed of a signal in the muon collider if the muon G minus 2 is there. Okay, so that's a motivation for muon collider, for instance. So I'm sure Tao will like it. Okay, so there is also a recent paper which gives the sensitivity from both the future lepton collider and from the high luminosity LHC and a muon collider. This comparison plot which can probe this leptophilic scalar parameter space, and how much luminosity you need to probe this leptophilic scalar parameter space. And it turns out that yeah, if you have the future lepton collider like E plus E minus, or if you have a muon collider, then you can really probe a large part of this parameter space in the in the electrophilic scalar. And this also could have some connection to these multi-lepton anomalies that I mentioned earlier. So both these multi-lepton anomalies and the mu-G-2, they can be correlated if you have this kind of electrophilic scalars. Okay, so I think I don't have time, so I'll skip this the LSND. So I'll go to the conclusion. So the standard ways to search for new physics have remained out of reach so far. So people have tried to look for inspirations from these small blips in the data or these anomalies as a possible alternative route to look for new physics. And I think it's still worth investing some time and effort, if not all, even though we know that the future is uncertain for these anomalies, but still we can have we can have some we can learn something from this, and we need to have a coherent effort and just and have active theory experiment collaborations and open access data to understand all the all aspects of these anomalies. And also I'd like to emphasize for the theorists that we need to find BSM scenarios that fit the data naturally. And it may not be your favorite model, but we should be open-minded and we should just look for all possibilities and try to see which one gives you the best answer. And also, moreover, we have to make predictions that can be tested so that we know if the model is testable or not. Okay, I think I'll stop there and take questions. Thank you.
Okay. Thank you very much, Bhupal. Very nice overview of a very broad topic. Again, to everybody, Bhupal will be around. If you have questions, you can ask him. But now I will give the floor to Suchita Kulkarni from the University of Graz, who will lead the next discussion session. Suchita, the floor is yours.
Okay, thanks very much. Bhupal, if you keep your slides up, because if there are any questions pertaining to your talk, it would be easier that way.
Sure.
I'm not, at the moment, I will not share anything from my side, right? Okay, so I do see there are quite a few questions. I would first like to invite Biswaroop, and I do see a question-answer question so in the chat, so we'll give a chance to you, Priyatosh, later on. Biswaroop?
Yes, thank you. This is about this lepton, PT distribution of dilepton or maybe trilepton events, which Bhupal you mentioned, and on which I have had discussions with Bruce off and on over the last 2 years. Now, very recently, Kaoru Hagiwara has written a paper trying to explain these events in terms of, or these PT distributions in terms of toponium production. Can Bhupal, Tao, or anyone else comment on this?
I think Bruce wants to
yeah, Bruce, can I come in? Can somebody unmute Bruce? Because
can you hear me?
Yeah, Bruce, go ahead.
Yeah, so as you know, we invited Kaoru Hagiwara about a year ago to South Africa, and we've been talking to him about that for about a year. And I'm very happy to see the preprint coming out. We've been having discussions for, intense discussions, I would say, for the past few days, where we explained to them that the anomalies appear in opposite sign leptons with low BJ multiplicity, which will not be explained by TT bar events. So following our conversations, what we did is we made a study of what would be the impact of low mass TT bar events, which is what he is suggesting. So, and of course, we would never describe 3 leptons or same sign leptons or the TTW X's and the ZW X's and all those things will not explain. This is pure TT bar modeling. But I think what's important here, and I want really to, I really want to appreciate Kaoru's effort and also his collaborators, Benjamin Fuchs, is that people are already realizing that the Monte Carlo mismodeling can't explain this kind of excesses in these corners of the phase space, because the Monte Carlo works well everywhere. The moment you mess with Monte Carlos, you basically destroy the entire picture. So I think in some sense, Kaoru's study is a very good demonstration that people are already giving up on the fact that Monte Carlo mismodeling is behind this. So I'm very happy that they are thinking along those lines, and I'm very happy to see they are proposing to the experiments to look at areas where we don't see the excesses, which is look at 2Ds with low mass, so that they can determine whether the toponium is really in the data or not. But thanks, Vishnu.
Thanks. And just one more question. So does this anomaly exist or not anymore now that this Monte Carlo error is factored in?
No, the anomalies have been growing ever since. In fact, there's few papers that came after that. We published a paper in PLB where we ran in more detail the calculations of the TTW cross sections to ascertain that we haven't missed anything. And there's been measurements from the Atlas collaboration of the WW cross section, which were not included in there. And also there's been a revamping of the entire measurement. No, it's not covered. Absolutely not. In fact, the significance is way, I mean, we are not talking about significance anymore. So we should be talking about other things at the moment. But that being said, I think the toponium is a very interesting thing that the experiments need to be looking into, and there are control samples that can be defined in order to ascertain whether the toponium is there or not.
Okay, thanks. I'll discuss privately more with you.
Sorry, somehow I got muted. Sorry, Priyatosh, I think you have a question. If someone can unmute Priyatosh. Priyatosh?
I allowed him to talk. In principle, we should be able to talk now.
Yes, I'm just trying to see if we can hear me. Priyatosh, can you say something? You have to. Okay, it seems Priyatosh, somehow we can't hear him, so I'm going to read out his question so we can answer it.
He has unmuted himself, so in principle, he should be able to speak now.
Can you hear me now?
Yes, we can hear you. Go ahead.
Okay, fine. So Gopal, thanks for a nice talk. So my question is rather generic. It's about the first part of the question is that do you have a preference in explaining muon J-2 when you consider scalar and vector leptoquark? Like there are set of models or one model? This is the first question.
Yeah.
Yeah.
Okay, let me try to answer that first before we go to the next question.
Yeah.
I might forget the next question. Okay, so let's see. Yes, so you can explain it using both scalar and vector. But as I said, so for vector leptoquarks, I mean, I find them a little bit trickier simply because we need some UV completion for the vector leptoquark model to be valid. And I mean, of course, there are some UV completions. I don't know if Andreas will talk about any of them, but yeah, I find the scalar leptoquarks easier to handle theoretically. So yeah, I think I don't know if that answers your question.
Yeah, and another question is that I guess that probably if the leptoquark decays to the top quark mode, I mean like up quark mode rather than the down quark, then that also helps, right?
Yeah. So yeah, for instance, we have this R2 leptoquark, which has two components, omega 5/3 and omega 2/3. So the omega 5/3 that will couple to the top sector, and then omega 2/3 that couples to the down sector. So usually we assume both of them to be degenerate because there are constraints like from theory, like you have the perturbativity constraint, you have the unitarity constraint, so you cannot really have them. You cannot have them too much mass split. But yeah, from the electro precision data. Sorry. Yeah, but you can have them a little bit mass split, and then I mean, it might be something interesting to look for comparing the top sector versus down sector.
Okay. Another the second part of the question. See, there are SUSY papers mostly which try to explain the muon G-2 as also the electron G-2, the cesium one, right, the negative one. But is it possible in the leptoquark, or is not at all possible to address both of them?
Yeah, that's a good question. So at least we couldn't do it in this particular R2 leptoquark model. We tried a lot to explain both electron and muon, and we could not do it. So yeah, again, this is just simply because one of them is positive, one of them is negative. So for that, you have to either go to like a loop level effect, like a higher loop level effect, or you have to have some kind of funny flavor structure, some kind of cancellations happening, so that this is, and this is very non-trivial.
So even if you take the off-diagonal Yukawa, it's still not happening.
Well, the problem is that you have to satisfy the LHC constraints as well, right? So, and as you saw, most of these constraints are very severe. So you cannot really have large off diagonal in one case and suppress it in the other case.
I think Andreas.
Yeah, sorry. Yeah.
Go ahead.
Yeah, I just wanted to say something about anomalous magnetic moment of the muon and electron leptoquark model. So the problem is not the opposite sign, because you have a chirally enhanced effect, so you have a free sign. The problem is that you violate mu to E gamma by orders of magnitude if you want to explain both of them at the same time with the same leptoquark. But now you should also take into account that with the new measurement of alpha, there is no G-2 electron anomaly anymore. So, you know, there has been something like 3 months ago, a new measurement of alpha from rubidium instead of cesium, and it's in 5 sigma tension with the old measurement. So I would say we just don't know which one is correct. And now, if you believe this, instead of a minus 2.4 sigma or so, now you have a plus 1.5 sigma in the anomalous magnetic moment of the electron.
Right.
So something exciting to look forward to, I guess.
Yes, yes. Very nice discussion. So yeah.
No, I had to say it now because I don't have the time to cover it in my talk. So.
Okay, good. So it's good that we have this discussion now in that case.
Okay, thanks both of them. Yeah, I think I'm done. Yeah. So.
Okay, very good. So just to chime on this from concerning the G-2. At least from what I saw, the LATOIL conference seems to have an update on the G-2 research. So it will come in about 10 days or so, if the program is to be believed. So something to keep an eye on. Highly exciting times in this context. Rohini has a comment. Rohini, can you go ahead, please?
Yeah, thanks both to Bhupal for a nice talk. And actually the question is perhaps jointly to Bhupal and also to Andreas or all these people who work on the leptoquark solutions, is Bhupal went to some extent in RPP violating SUSY corners, but I want to know whether in general scalar leptoquark can be most of the time looked upon as possibly SUSY, RPV SUSY, or there are only some corners where it can be done, because in terms of low energy properties, RPV SUSY, many couplings are ruled out, constrained quite strongly, which was first done by Tao a long time back. So I guess it's a joint question to all the people who use leptoquarks to explain the B-quark anomalies.
Right. Yeah. So yeah, in general, like for the scalar leptoquark, it comes from different models. So RPV is just an example, but I find RPV SUSY kind of a very well motivated scenario.
For me, yes, that's why I'm asking you this question actually.
Right. And yeah, so I agree that there are a lot of constraints, but also it seems like there is still some parameter space that is consistent with all the constraints. I mean, this is an example here. So of course, I mean, there are so many different couplings that you can vary. So just to keep things simple, so we can set some of the couplings to be equal, which I guess is reasonable. And then also with the reasonable set of mass spectrum for the spermions, it seems possible to satisfy all the constraints and explain both RD and RK. So this I think is interesting.
No, so I'm happy to hear. I mean, that's why I asked this jointly, because most of the time when I hear discussions of the anomalies, B anomalies, and people talk of leptoquark solutions, we of course go all over the place. We change the charges of those leptoquarks. And for me, having a model, very rarely, apart from your talks, I have not normally heard so much about RPV SUSY. And in the beginning of the days, people used to talk about it a lot, but slowly that has gone away. So I'm basically wondering whether this was a problem with some other sets of low energy constraints which had removed it, but you are telling me that it's okay. There is no real issue with this. Okay.
Right. Yeah, it still seems okay.
Thank
I think the other leptocoque models are probably a little bit simpler to handle because there are less number of couplings there.
Sure, sure.
Of course, we have more couplings, but still, I think we can make some educated guess. And then,
as you correctly said, I mean, for me, that attraction is that it's in a well-motivated model.
Exactly,
So that was my question. And the second question is not related to this, but actually, since you people were talking about toponium, I have not seen this paper of Kaoru, but can one not talk of any old TT bar resonance? Does it have to be toponium? I mean, this is maybe a question more to Bruce and Vishwaroop, perhaps. Any odd TT bar resonance, can we not use that?
Rohini, sorry. So I think if I may, I'm very sorry, but probably Andreas can comment on the RPV part first. So we complete
I wanted
that discussion.
to comment on the RPV part. Thanks a lot, because I also don't have the time to talk about this in my talk. I'm very sorry. So I'm happy to say it here again. I am a little bit more skeptical about explaining all these anomalies in the RPV case, because you don't have a SU2 triplet leptoquark. So there are also this bounds from B to D mu nu over B to D E nu. I think they are somehow not included in this plot. And then it's also a problem that your fit to RD star is not, you can explain RD star, but the total fit, if you also want to exclude P5 prime and so on, is not so great. So I agree that RPV SUSY is interesting in the sense that it at least you can get effects which go in the right direction. But if you really want to fully explain data, you need more than the minimal RPV SUSY. I mean, you can always extend the standard model and then make it supersymmetric or R parity violating, but really the minimal version of the MSSM R parity violation, I think you cannot fully account for all the anomalies.
Okay, thanks, Andreas. Thank you very much.
I once heard somebody say if you explain all the anomalies, I mean, not all the anomalies will come true. So if your model explains all anomaly, probably the model is wrong. So that's also something just on a little bit of a lighter side. Bhupal, you wanted to say something?
Sorry. No, I agree with Andreas that yes, you cannot explain the RD and RK actually at like 1 sigma, 2 sigma level simultaneously in this setup. Yeah, that part I fully agree. But maybe we have not explored the whole parameter space of RPV. That could also be the reason. I just don't know. I mean, this is one case where at least at like 3 sigma level it works. Now we can say, oh, the anomaly just like 3 point some sigma, so you're explaining 3 sigma, that doesn't mean much. Well, yeah, that could be true. But just that I find this framework very interesting, and it comes with all the goodies of SUSY, as Rohini mentioned. So I think, I mean, this is more well motivated than a vanilla leptoquark scenario where you just add a power coupling and you try to explain. So I mean, this is a personal bias, I would say. But otherwise I think that the generic leptoquark does better job at explaining than the RPV SUSY. I agree.
Thanks, Bhupal. So concerning Rohini's second question, which was related to the TT bar resonance, if Bruce would quickly like to comment, because we do have a few other questions lined up.
Can you hear me?
Yes, we can.
Right. So the rationale behind Kaoru's introducing toponium is because the discrepancy between data and Monte Carlo are located for masses of the dilepton system. In the dilepton case, of course, doesn't explain the others, of course, below 100. So that's why he felt that, well, the toponium will create, because it's basically a small mass, the TT bar system is very small. It's a threshold that it would enhance the production of leptons at a small delta phi and small masses. Again, that will only be the case for high Billiard multiplicity. Now, when people look, there's been quite a number of results from ATLAS and CMS looking at TT bar resonances. I think there is a discussion pertaining to the threshold area. I mean, that we can discuss. But all in all, once you are above the threshold, the data is relatively well described by the Monte Carlo, because there you have very well-defined topologies, high PT objects, and all that. There's also discussion. There's been a paper by the Barcelonians where they also point out to a nexus in the 4 top searches. But again, as we know, once you see a signature for the first time, you always see a signal strength above 1, typically, because you pick the upper fluctuation. So we need to look at those with more data. But all in all, when it comes to TT-bar resonances, there are strong constraints from actors and CMS.
I had one quick question again, Bruce, onto this. Is that, does the spin of the resonance make any difference?
I have to think about it. I have to look at the literature.
Okay. Okay.
Yeah, to look at it. Yeah, I
right.
cannot answer.
Thanks. No, but thanks for this discussion. Thanks.
Good. I'm very sorry. Viswarup had a comment about the leptoquark versus RPV issue. So I'm going to go back to that a little bit and give the mic to Viswarup. Viswarup?
I forgot to unmute. It was regarding RPV versus leptoquark. In response to Rohini's observation, I also have noticed this, that the tendency to explain things in terms of RPV has gone down a little bit of late. This, I believe, is more of a sociological issue. Most things that leptoquarks can do can be done with RPV, and with these additional bilinear terms, the potential goes up even more. However, the very fact that RPLAT violating supersymmetry apparently steals the possibility of having a dark matter explained in the supersymmetric framework has made people less enthusiastic about RPV now. So that's why I call this is not entirely true, though. One can still have dark matter and RPLAT violation, but this is what I call a sociological issue. This is, of course, an observation which is not strictly scientific, so people are free to ignore this. And Bruce, about this Rohini's question that this PT distribution of leptons, whether it depends on the spin of the resonance, I guess it is, because the angular distributions will be seriously affected by this. Angular direction, handedness, all these issues will conspire. And I suspect it will have something to do with the PT distribution of the dileptons. Anyway, thanks.
Thanks, Viswarup. I think something to look forward to. Rohini, do you still have a Nima? Can you please unmute yourself?
Yeah.
Go ahead.
I just wanted to say, I just have to step out for a second at the beginning of the question session, so maybe someone said it already, but I wanted to heartily second the idea of having some place on the web or somewhere else, or some accessible place where all the anomalies are listed, and every whatever's known about them can be accessed. A long time ago, I thought that this would be a great thing for the PDG to do, which is even forgetting about anomalies, the PDG could have as sort of part of what it collects about what we know about particle physics, limits on higher dimension operators. I mean, that's after all something we know about particle physics as we learn more. Anyway, that together with a listing of all the anomalies would be maybe not with the PDG, but somewhere I think would be totally awesome.
Yes, I think this is a kind of a project that one could indeed think about doing.
I think it could be a forum, you know, it could be part of the forum that Bruce and Oliver have started. One can think of that.
I would like to also hear from experimentalists if anybody has opinion about this, because anomaly chasing, making sense of.
I mean, can I make a little practical?
Go ahead. Sorry, go ahead.
Can I make a little practical comment about this? I mean, on the theory end, this is a really ideal thing for like very, very bright undergraduates or beginning graduate students. So you don't have to. It doesn't have to turn into something which is what you do for your whole life, and you don't do it. You know, but but thinking about anomalies and thinking about, in fact, where we get the limit on higher dimension operators. I mean, I mentioned these two things because they're both sort of frontier things about what we know about the world, right? You know, either at the level of limits or at the level of hints for something else. And tracking down, thinking about the anomalies and figuring out where the limits on higher dimension operators is coming from. I cannot imagine a better way for like a young, you know, theory phenomenologist to learn physics than actually doing that. So I think that you don't, one doesn't even have to turn it into something which is, anyway, it's an ideal thing for like, you know, a summer project, some brilliant undergrad or for collections of grad students. Anyway, I think it would be awesome. I think it would be really, really great. So thanks for bringing it up, Bhupal, and I really heartily second it.
So yes, I think Bhupal has already given us a starting point on his slide by collecting all the resources. Somebody from the audience had their hand up. Benjamin. Bhupal, sorry, I'm going to hold on, asking you to speak. Benjamin?
Okay, I was muted, sorry. So a very quick comment on the previous speaker. So I clearly haven't kept track of the field, but the analysis of anomalies started as analysis of effective field theories and effective operators. And as it matured, people started to flesh it out in terms of specific models. Now, more recently, people have tackled the question of just trying to do a very global fitting to any kind of, you know, effective field theory in a general setting. And you can do that, but the problem is there are too many handles to do a reasonable fit to everything simultaneously. So you end up just trying to fit a couple of Wilson coefficients at a time. And then in that sense, it's very restricted. So those, I mean, this is not new. It's something that people have been doing. And now we have a fairly good grasp. So just check the literature. There's a lot of it there.
Sounds good. Thanks for your input, Benjamin. Bhupal, you wanted to go back to the discussion of the collection of anomalies, I believe.
No, I think yeah, I think it's good to get the community support on this, and I think yeah, maybe PDG is a good idea, or just some other kind of forum where this can be done. So that would be really useful to the community, I think.
Right. So I think this is something Andreas also agrees on the comments that we should discuss it maybe at the end of this workshop or so to consolidate this if possible. And yeah, it would indeed be good so that somebody doesn't have to spend weeks looking through the data and finding out what's going on with each of these aspects. Nimas, do you still have a question? Your hand is still up.
No, sorry about that. I should just lower it. Sorry about that.
No problem at all. Okay, good. Are there more questions at this point? Because I don't see any hands in the audience raised. I also assume that we all are a bit eager for having our coffee. I just wanted to add one comment on my side, which was brought to me actually via a discussion from Twitter, is that alongside of all these anomalies, we also have recently observed some peculiarities about contents inside the proton. And we will have these sequest, spin-quest experiments, which are going more along those lines. I'm certainly not an nuclear physics expert to actually know a lot about it or comment about it, but there seems to be something interesting going on also on the nuclear physics side from the point of view of proton contents or so. So I don't know if anybody is more updated on this than me and would like to comment on where these can go. If not, that's an anomaly that we should definitely try to keep in mind.
Yes, thanks for bringing that up, Suchita. Yeah, I was not aware of this. So yeah, if there is an expert who can comment on that, that would be great.
I am not an expert, but I can just tell that as what everybody else must know by who reads science alerts, that the D bar, the ratio of D bar to U bar in a proton is, which we expect by isospin symmetry or charge symmetry to be 1. To large extent, by doing experiments on deuterium and proton hydrogen targets, people have shown that d bar over u bar is different from 1 over a considerable range of the Bjorkenx. But if you look at it, right now it seems like an issue of non-perturbative nuclear physics to me, because it's a question of what gives rise to this isospin asymmetry in the d bar and u bar, what generates it, right? I mean, QCD has some idea how it is, how the u bar and the d bar content is generated. We think it's because of the gluon splitting, and then that we expect to be the same for u bar and d bar. But if the fact that the proton has 2 up quarks and 1 down type quark, which at the original non-perturbative low scale level itself gives rise to some difference between the momentum distribution of d bar and u bar, that's not so clear. In fact, there are nuclear physics models, one by Miller and somebody, and there are also the statistical models of nuclei, neutrons, and nuclei, nucleons, which people try to predict these differences also. So for me, it's a pointer to study the non-perturbative aspects of proton physics. At least that's my understanding of this Nature paper.
Right. Tauhan, you wanted to say something?
No, sorry, I just got back.
Okay,
Another
good.
meeting.
Good. Okay. Right. So we were just discussing about the latest proton substructure research, and the need to basically also talk to communities which do nuclear physics, which do lattice physics and things like that. So we have a better understanding of anomalies in that direction.
Yeah, thank you. In this regard, I may want to make a comment. I really like the tables that Bhupal summarized, just like on the screen. I think out of this conference, maybe we can do a more systematic list. We probably can list all these the potentially interesting anomalies vertically, as Bhupal is doing, and we probably can list the possible probes from different experimental aspects on the horizontal axis. So we can exchange. We just remember, Bhupal, we had this meeting in Europe in place for the neutrino physics. We did the same thing. We said, so there are so many interesting possible observables that may lead to some possible discoveries. Now you listed them for the anomalies. Then you made a few good examples, like the operator can be twisted into the collider search. That's a really important complementarity. This is a very important thing for us to systematically do this. And certain experiments may be more sensitive to this, and given the scale. Could we try to consider to exchange your tables into a more systematic list? Vertically, we list as many interesting observables anomalies as possible. In the horizontal axis, we list all the possible potentially durable experiments that have been thought out or haven't been thought out.
Yeah, I think that's a very good suggestion, Tao. Yeah, it would be nice to have all the observables that could be probed. And maybe one observable can probe multiple anomalies. So that's really important to.
So I think it nicely complements with what we were discussing earlier, which is to keep this repository of anomalies. We do have a comment from the audience. Leandro basically suggests that we could add forward-backward asymmetry of the bottom at left to the list. So there is one more candidate on the list that we can keep on. To the organizers, I think we are quite a bit over time at this point. Would you suggest that we wrap up this session?
So I would suggest that we start in 4 minutes of Andreas' talk, and the remaining time, I mean, if there are still questions and the discussion keeps going, I mean, we can keep it up for the next 4 minutes.
Sounds very good for me.
Yeah, we simply skip the break, seeing that we can get coffee anytime we like. There's no need to have a dedicated break for that. So you have, if there are more questions from the audience or from the panelists, then we can keep going. I will, or let's just keep an eye on the time. 4 minutes.
Thanks, Oliver. Sounds very good. Okay, just check Mattermost if there are any questions. So I just wanted to see if audience has any further questions at this point. Okay, so if not, right, one of the questions that I ask myself when I'm looking at the anomalies and the studies of anomalies, one thing I like personally when we are chasing these excesses is the potential it has to give direction for doing new physics studies. One of the examples that I kind of personally like is what comes from astrophysics, which is these discrepancies in the large scale structure in terms of core cusp issues, and that give rise to the self-interacting dark matter scenarios, which are highly popular and very well studied currently, both in simulation as well as any associated collider signatures that we could have. And similar to that, one thing that we could discuss in the next couple of minutes is the broad classes of scenarios that we would want to put on our plate going forward while keeping an eye on the landscape of anomalies. So I think Bhupal, you highlighted a couple, the leptoquarks, for example, or the RPV scenarios. Are there also scenarios from neutrino sector that could be interesting going forward?
Yeah, certainly. Yeah, for example, if you have sterile neutrinos, that could fit into some of these scenarios. I actually skipped some of the slides where I had discussed one of that. Maybe also Oliver can comment on that because he has worked on this. So yeah, I think yeah, we could come up with some generic scenarios which can fit as many of these as possible, rather than just going individually model by model. I don't know if I addressed your question.
Sure. Since you roped in Oliver, I would like to know if he has something to add. Sorry.
No, not at this point.
Okay. So one thing that comes to my mind, Bhupal, was this Koto anomaly that you skipped very quickly over that has a connection to heavy neutral lepton, I believe. Not at the beginning, but towards the very end, when you skipped over the slides, you had explanation of Koto anomaly from HNL searches, right? Or from heavy neutral lepton decays.
Sorry, you mean
so
the
that's slide 60, slide 26?
Yeah, so this is the LSND.
Sorry, LSND, I'm sorry, yes. I got confused. So does this have any implications for a high energy collider, or is this an entirely low energy explanation?
Again, so this is the work of Oliver, so maybe he can comment on this. But I think the heavy neutrino, you need to have this minibone explained. That's I think in the like multi MeV to GeV range, and that doesn't have any direct implications for the high energy colliders. But if it's coming from part of like a UV complete framework, so if you have for instance 2 or 3 heavy neutrinos, then you can have some of them heavier, and they could have implications at the high energy colliders. Like you can have the lepton number violating signals. If they're Majorana particles, then you have semi-sign dilepton, for instance. So yeah, so in a bigger framework, it could have an impact on the high energy colliders, but just by itself, this is too light for the high energy colliders.
Thank you.
Can I make an obvious comment, guys?
Yeah.
Just to say something, just to repeat something I was saying before. I mean, I think that if we want to make the sort of study of anomalies as a general thing, a more systematic thing as well, and to slightly avoid some of the things some of the sociological things you're saying at the beginning, that, well, it's all ambulance chasing and they all go away and so on. I mean, explaining the anomalies and putting limits on higher dimension operators are very closely related things. And the limits on higher dimension operators are sort of permanent facts about the world that don't go away. You know, they're just true. And of course, if you see an anomaly, you try to explain it, which is great. And that's why I think they should be they should go hand in hand. They should be part of the same. They should be part of the same venture. And if we collect everything together, I think that's why it would be useful to sort of put these things together, because they really are just some summary of what we know today at the frontiers of our high energy knowledge. And this is related to one of the previous points. There are some things. There are some higher dimension operators which we haven't seen yet, but of which we do see would immediately tell us a relevant scale for colliders. For example, that's one of the great things about electron-electric dipole moments, as many of us know. The kind of, if you see an EDM in the next round of experiments, then it's associated with a scale that's maybe 10 or 100 TeV, not the gut scale, not some super far away scale, but it's with a very accessible scale. And so if you see it, it's a precious lifeline for where the next scale of new physics is that we might actually be able to see with the collider. So both explaining anomalies as well as just putting limits on current higher dimension operators are both sort of opportunities for where to look next if you see something. And so anyway, so I think it's useful to sort of imagine these two activities as part of the same thing. Yeah, anyway, it's a totally trivial comment, but I thought I'd make it.
Thanks. Okay, Suchita, thank you very much. I'm taking over.
Sure, I think, yes. So I was just going to wrap up saying, I think on that note of keeping an eye on future, it's time to wrap up the session. Oliver, back to you.
Thanks. So good comment. We always have to look at the future. So yeah, you might have noticed we skipped the break time. So if you need need of a coffee or dinner or whatever it is appropriate where you live, please go ahead. We will continue with Andreas in the meantime. Andreas Krivelin on the lepton flavor universality violating anomalies. Okay, Andreas, the floor is yours.
Okay, now you can hear me?
Yes, I can hear you.
Okay, great. So, okay, very good. So thank you very much for the invitation to this amazing workshop and the opportunity to talk about lepton flavor universality violating anomalies. So I will in some sense continue where Bhupal left us, and I will focus on his first 6 or 7 bullet points which he has about lepton flavor universality violation. This is of course closely connected to PSI here. As you might know, we have MAC and the mu3e experiment, and now since I'm for this year at CERN, you see it looks still similar, but again here at LHCb we are testing all these flavor anomalies. Now here's the outline. So first I start with the introduction, and then I want to give you a review over these hints for lepton flavor universality violation which we acquired. So we already heard in the talk before, there are several classes. It's this semi-leptonic B decays, it's the anomalous magnetic moment of the muon, it's tau decays, and interestingly, also this Cabibbo angle anomaly, as I want to explain you later, can be put into the context of lepton flavor universality violation. Then I want to briefly recall how one can explain each of these anomalies with new physics models. And then I want to briefly come to common explanations. So to be a bit more ambitious, not just explaining one of them, but several of them at a time, like we also already heard in the talk before about lepton quarks. And then I conclude. Okay, so here's the introduction. So first of all, of course, we all know we want to discover new physics. And there are at least 3 frontiers how one can do this. There's the cosmic frontier with cosmic rays, dark matter, dark energy. There's the energy frontier. Here, at the moment, we only have the LHC in principle, but we are all looking and hoping very much that we will get future colliders here. Then there's the intensity frontier, neutrino double beta decay, test of fundamental symmetry, Lorentz invariant, proton decay, and of course, which is the main topic here, flavor. And now what this diagram just depicts is that all of this is complementary. So it's not that by doing one, you take it away from the other, but it really helps of finding what kind of new physics could supersede the standard model. So if we confirm the flavor anomalies, this wouldn't be only great for the flavor physics, the intensity frontier, but for whole particle physics, because of course, these anomalies would have interesting implications for all the other frontiers. And you could also use them to build a convincing case for future colliders, because this new physics case must be at the TV or multi-TV scale. It cannot be at the GATT scale. So the main topic here is, as you see from the title, lepton flavor universality violation. So in the standard model, lepton flavor is conserved in the limit of vanishing neutrino masses, but this is really an excellent approximation. Even if you take into account the neutrino masses, you end up at branching ratios of the order of 10 to the minus 45 at most. So this means lepton flavor violation, even in a standard model with massive neutrinos, is in principle unobservable. But this has also a good point. Once you see it, you know this is definitely new physics. There's no other way. Concerning lepton flavor universality, all standard model gauge interactions don't distinguish between electrons, muons, and tau. So they are lepton flavor universal. In fact, the only interaction which violates lepton flavor universality are the Higgs-Yukawa couplings. However, the direct effect here is really small, because the tau has a mass of 1.7 TeV divided by the WEF of something like 170 GeV. So you only end up by a 1% coupling at most. So this is really small and in principle negligible in all processes. But what is not so small is the indirect effect via the masses. So of course, the Higgs interactions give rise to the lepton masses, and they can be important because they lead to phase-space effects in decay. However, when I talk here about lepton flavor universality violation, I really mean violation at the fundamental level of couplings. So phase-space effects are always already taken into account when I talk about lepton flavor universality violation. Now, this is all about leptons, so we don't have problems with QCD and unperturbed effects, at least in most cases. So, and because it's conserved by the standard model gauge interactions, lepton flavor universality is an excellent probe of the standard model. Here, I already briefly show you all these anomalies again, which point towards the violation of lepton flavor universality. And now I want to go through them each by each and explain in a little bit more detail what they are. Okay, so the first one, as we also already have briefly seen, are these hints for lepton flavor universality violation in the neutral current B decay, so B to S, L plus, L minus. Now, bottom and strange quark have, of course, the same charge. This means it's a flavor changing neutral current. And like all flavor changing neutral currents in the standard model, because the CKM matrix is the only source of flavor violation, it must be mediated at the loop level. So this is strongly repressed already in the standard model, and therefore also very sensitive to difference. Now, what you do here, you construct these ratios Rk and Rk star as B to K or K star mu mu over B to K E E. Now, this is a semi-leptonic decay. So in principle, you are sensitive to the form factors. So to Q squared, to momentum transfer dependent quantities, which describe the transition from a B meson to chaos. However, so it's in principle difficult to calculate them because you need unperturbed methods. However, in these ratios, it drops out to a very good approximation, because compared to the B and K on mass, you can really neglect the muon in the electron mass. So this is also the reason why here for Rk, the standard model prediction, which is this dashed line, is thicker than the uncertainty. So this is really great. For Rk, it's a little bit more difficult because of the photon pole here, but in principle, it's the same. The standard model prediction is really clean. And what you see here is you should focus on this black cross from LHCb, which is really dominating all these measurements. And you see something like a 25% deficit in muons compared to electrons. And this is also supported by this lambda b measurement, even though not so precise. But if you combine all of this, you already end up for hints for lepton flavor universality violation in BDKs, which are more than 4 sigma. But now there comes something really interesting, namely that also in observables which don't measure lepton flavor universality violation, simply because we only know the muon mode, because it's much easier to measure them, you also have found hints for for new physics. So among them, there are many, many observables. The most important one are B sub S to mu, B sub S to phi mu, but also this famous angular observable called P5 prime in B2K star mu. Here, the significance alone is already quite high. And now the crucial point is, if you perform a combined fit to new physics, so you take this lepton flavor universality violation, but also all the other observables you have. And for example, you assume that there's new physics in muons only, you get an excellent fit to data. So you improve in the observables which disagree with the standard model, but you don't mess up observables which agree. I mean, this is absolutely not clear from the beginning. And it's also not clear that with turning on, for example, 1 or 2 Wilson coefficients here, so just this parameter giving you the effective interaction strength of B quark with strange quark and lepton pair, you can really do this. I mean, it could easily happen the other way around. You make one anomaly better, the other one worse, then you wouldn't get such a good fit. But it seems like that all these measurements are consistent with each other. And therefore, if you look at this plot here, so here there are these Wilson coefficients. They already have the standard model value, but we assume here that they get in addition a new physics contribution. And then you see here that you are quite away from the standard model point at 0, 0. So this is 1 sigma, 2 sigma, 3 sigma, 4, 5. So you can more than 5 sigma better by combining completely different measurements. And I think this is really astonishing. And this gives at least me some confidence that there could be really some new physics behind this B2S transition. For B2 theta or new transitions, it's a little bit different. So also here, you test lepton flavor universality, the charge current, but you compare tau modes to the modes with light lepton. This is already mediated at 3 level in the standard model, so it's much more difficult to get a new physics effect here. And also reconstructing taus is quite difficult. And here in these ratios, you cannot neglect the tau mass because 1.7 GeV is not negligible to the B mass of something like 5 GeV. So this is why the form factor dependence doesn't drop out exactly. So you have this cross here for the standard model prediction, which has still a reasonable error, I would say. And if you combine all these Bell, LHCb measurements and so on, you end up at this red ellipse, which is nearly exactly 3 sigma away from the standard model prediction. So again, it is quite remarkable that all these measurements are above the standard model prediction. And again, it's also supported by this R-shaped psi measurement of B sub C to tape out tau nu or B sub C to tape out tau nu. However, as I said, it's 3 levels, so you need a huge new physics effect. It's not easy to explain it, but one can do it. In order to explain it, you need a 10% constructive effect. Okay. The next observable is the anomalous magnetic moment of the muon. Here in the standard model, this deviation from 2 is generated by diagrams like this. The theory prediction is challenging, mostly because of these hadronic effects here. So here, people have calculated 5 loop diagrams. Of course, this is also really difficult to do it, but this has been done. And so electroweak effects only are really under control. What is causing some problems is everything related to hadronic effects, like here, this diagram showing hadronic vacuum polarization. However, there was recently reached a theory consensus, and the theory consensus gives you exactly a 3.7 sigma deviation from the standard model prediction. Again, the new physics you need here is not small. It's of the order of the electroweak effect in the standard model. So of the order of diagrams like this here. And this also means that if you want to do it with new physics at the TeV scale, you are already suppressed by a factor of 100 compared to the standard model. So you need some enhancement to compensate for this. This is in fact possible with what is called chiral enhancement. This you need for heavy new physics. It just means that you don't do the chirality flip with the muon mass of the standard model, but you do it with an order of 1 coupling to the Higgs boson, and then you can get this enhanced effect. Since the deviation from T-2 vanishes exactly for a muon mass going to 0, in fact, this observable is directly measuring the violation of electron flavor universality. Right? Okay, something less known and also less significant, but I think it's still very interesting in the context of what I have shown you before, are these decays tau to mu nu and tau to e nu. Here again, you can build 3 ratios, and what you see here is that the tau to mu mode is somehow enhanced over the expectation. Taking into account correlations, what you end up here is that you could have a new physics effect in tau to e nu, but you really want to have a new physics effect in tau to mu nu at the 2 sigma level. Finally, there is the Cabibbo angle anomaly. So what here happens here, the origin is that you determine VUD, most precisely from super-allowed beta decays, and then you compare it to VUS from kaon and tau decay, assuming CKM unitarity. So if I don't have new physics, the CKM matrix is definitely unitary, and you can convert everything in units of VUS. And then what you see here is that beta decays with different radiative corrections give you significantly higher values for VUS than kaon decays, or these KL3 decays, or even tau decays. Now you can also reverse this and say, I can use this to test CKM unitarity. And this is in fact what the PDG does. And here what you find is a 3 sigma deficit in CKM unitarity, whose origin is exactly this disagreement between VUB from VIS from beta decay versus VUS from kaon and tau decay. So here we have the 3 sigma tension. Now, you might ask the question, what does this Cabibbo angle anomaly have to do with lepton flavor universality violation? I was talking about the CKM matrix, so about quark physics. Now, here this comes. So let's assume a modified WLU coupling. Here, this is just the standard model Lagrangian for the W coupling, and here you introduce the small correction epsilon. Now, VOD from beta decays depends on the Fermi constant and also on this correction to the W vertex. The Fermi constant is determined for muon decay, and it has a dependence on epsilon EE and mu because in muon decay you have, of course, muon and electron. Now, the dependence on the electron correction cancels, and you are left over with a dependence on the muon correction, which is even parametrically enhanced by the CKM elements, which gives you a factor of 20. So here, if you look at VOS from kaon decays versus VOS from beta decays, this is modified by epsilon mu, and so with non-vanishing values, you can get them into agreement. You also have tests from other observables with lepton flavor universality violation like R pi or K to mu nu or K to E nu, but you see here this all works well. So this tells you you can in fact interpret the Cabibbo angle anomaly as a sign of lepton flavor universality violation. And then if you look here at this compilation plot where you can see these different anomalies, I think it's reasonable to put it into this context because this allows, at least in principle, for combined explanation. So the picture, what we see here is that we have big new physics effects in everything related to tau. So with big, I mean big compared to the standard model amplitude. Even so, the significance is limited because data with tau is not so great. For muons, we have medium-sized new physics effect compared to the standard model, and the significance is highest just because data with muon is so great. With electrons, we don't really know if there's a new physics effect. Maybe there is, maybe there is not. But what is also interesting is that in these decays where bottom quark decays to first generation quarks, also here there are some slight tensions compatible with the global picture. Okay, so this was the overview on this leptoflavor universality violating anomalies. Now let me come to new physics explanations of these anomalies. So how can I extend the standard model to account for these measurements? For RD star, it's both difficult and simple at the same time. You have to complete with a tree-level effect in the standard model, so you also need tree-level new physics. You could do this with a charge Higgs, W prime, or a leptoquark. There are really not more possibilities. Charge scalars don't work well because of problems with Q-squared distributions and the B sub C lifetime. W primes have problems with direct LHC searches, both if they are left-handed and if they are right-handed. If they are left-handed, they come together with left-handed Z prime, and you get problems of S-channel production. If they are right-handed, you need right-handed neutrinos. They don't interfere with the standard model. You need huge couplings, and again, you get problems with LHC searches. Leptoquarks give strong signals in tau-tau searches, but as you have seen in the talk from Bhupal, they still work. So in principle, at least if you want to go for the central values, leptoquarks is the only way you can do it here. For B2S mu mu, it is simpler because you only complete with a loop suppressed effect in the standard model. So what people tried a lot is Z prime. I only gave the very first reference here. There are hundreds of articles on this. The Z prime works nicely, but it gives you necessarily an effect in BS mixing. So you can imagine here, you take this left-handed side of the diagram, you double it here, and you have a tree-level contribution to BS mixing. This is significantly constraining this coupling to BS, but if the muon coupling is much larger than this coupling here, you can still do it. You also can produce the Z prime at the S channel at the LHC. This already requires that you have reduced couplings to first generation quarks, but again, you can do it. There are also several possibilities how to explain B2S mu at the loop level. Scalars like fermions, doublet models are to leptoquarks, and prime couplings only to tops. What works very easily, maybe even too well, is if you just add leptoquarks. You get a tree-level effect where you want to have it. You get a loop suppressed effect everywhere else. So you perfectly explained anomalies without being in conflict with other data. However, if you only want to explain B2S mu with leptoquark at tree level, it's also in this sense not so exciting because the predictions are quite weak. You need really extreme precision somewhere else to find it. And now explaining the anomalous magnetic moment of the muon, of course, in the MSSM with tangent beta enhanced lepton loops. This was always in the past, it was said, anomalous magnetic moment of the muon is the smoking gun for the MSSM. There are so many references, I didn't dare to mention them. So this is still possible, but as you cannot have a universal scalar sector anymore, because otherwise LHC constraints are too strong. You can do it with light scalars, with enhanced muon couplings, Z primes, which are either light or have tau mu couplings, heavy new scalars and fermions, and again, leptoquarks work very nicely. And here it's really great because you can do the chirality flip with the top mass. So you have an enhancement of the top mass over muon mass 1700, so even with multi-TV leptoquarks, no problem at all explaining T-2 of the muon. As Bhupal also told you, this predicts some nice effects in Higgs to mu, but you can also correlate it to Z to mu, which you can then measure at future colliders. So the orange region is what you like to have from the anomalous magnetic moment of the muon, and the green region is the sensitivity you can get at future colliders. So you see, if this blob here overlaps, then it's a viable solution. If it doesn't overlap, it's not. Okay, how do I explain the Cabibbo angle anomaly? As you have seen, before you can do it with modified W mu coupling. You could also still do it with modified W U decoupling, so violating at least apparently CKM unitarity in case there's a fourth vector-like generation of quarks. Tree-level effects in beta decays are disfavored by LHC searches. W prime mixing still works. What really works very nicely are vector-like leptons, especially if you have an SU2 singlet coupling only to electrons and an SU2 triplet only coupling to muons. The point in this case is you don't only explain the Cabibbo angle anomaly, you also improve the global electroweak fit. And then if you look here, you have 1, 2, 3, 4, 5, more than 5 sigma improvement compared to the standard model hypothesis. For tau to mu nu, again, many possibilities exist. For example, a gauged mu minus L tau set prime. Here you do it via box diagrams, lepton flavor violating set primes, modified WLU couplings, a W prime, or a singly charged scalar. A singly charged scalar here is nice because due to hermiticity of Lagrangian, it only has three free couplings. And with one of them, you can explain the Cabibbo angle anomaly via a shift in the Fermi constant, and with the other you can explain tau to mu nu. And then you predict nice lepton flavor violating effects in tau to e mu mu and so on. Okay. In the last, I have something like 5 minutes left, right? In the last 5 minutes, let me come to simultaneous explanation. So a vector leptoquark can nicely explain RD star together with B2SLL data. And in fact, there's an intriguing interplay between loop and tree-level effect. Unfortunately, I don't have to go the time to go into details, but what is really intriguing is that this yellow egg here lies exactly on top of the blue band preferred by B2 theta nu without violating any other band. If you don't calculate it, this is not given for granted. This egg could lie anywhere else. So this is really nice. And the vector leptoquark with the correct quantum numbers is exactly the one of the Partisalam leptoquark, which offers the nice possibility to somehow combine it with unification of lepton number and count. For explaining the Cabibbo angle anomaly together with B2SLL data, you can use a heavy vector triplet, SU2 left triplet. So here, then you get these blue regions from the electroweak fit plus lepton flavor universality. The yellow regions are from B2SLL, and they nicely overlap here in this red region where you can again explain everything. So this is also not granted. Assume the yellow region would be here, then it wouldn't give such a nice fit. So this is a possibility for common explanation here. And the last model I wanted to explain you is one which can even do more. It can do B2SLL Cabibbo angle anomaly. Also, which I didn't mention so far because it's not directly related to lepton flavor universality violation, is the forward-backward asymmetry in set to BB bar measured by lab. And again, tau to mu nu over tau to e nu. So here on the left, you just see the representation of the standard model particles under the standard model gauge group and a new U1 prime, which is in fact a mu minus L tau symmetry. What I do is to this model, I add two pairs of vector-like quarks here with the quantum numbers of a doublet, with the quantum numbers of a singlet, a singly charged scalar, and a singly charged singlet. Now, these vector-like quarks, they mix with standard model quarks after electroweak symmetry breaking. So they give rise to modified set couplings, where the modified set couplings related to right-handed beats can account for the set to BB bar forward and backward asymmetry. You might also need a small left-handed mixture, but that works. And I can generate via a loop effect a set prime coupling to BS. And then this model has some quite nice interplay. So I have this pair of vector-like quarks, this new Z prime, and this singly charged scalar. The singly charged scalar together with the Z prime gives rise via the Z prime penguin to effect in B2SLL. The mixing of the vector-like quarks with the standard model quarks gives you again Z prime penguin and the modified ZBS coupling. Then the vector-like quarks explain Z to BB again via the mixing. The Z prime gives a box effect in tau to mu mu. In fact, it doesn't give a box effect in other leptonic decays. And the phi plus gives you a tree-level effect in the Cabibbo angle anomaly, and only there because of the mu minus a tau charge assignment. So I would say for explaining 4 anomalies, this model is quite minimal. And here you just see it nicely works for B2SLL without violating bounds from BS bar mixing for vector-like quarks around 2G, 2 TeV, a singly charged scalar mass around 1.5 TeV, while this here is excluded by LHC searches. Okay, so this brings me, I would say, even in time to my conclusion. So you have seen all these hints for lepton flavor universality violation: RD star, Cabibbo angle anomaly, B2S mu, the anomalous magnetic moment of the muon. And now these anomalies point towards different extensions of the standard model. The thickness of the error is my very personal prejudice, how strongly they point towards such extensions. And as you have seen here, for example, you can combine also a W prime and a Z prime in a triplet, which allows for nice combinations. But anyway, if you confirm or disprove some anomalies in the free future, this will bring us much closer to what model could supersede the standard model. And again, I would really like to stress, if these flavor anomalies are confirmed, this would be amazing, not just for flavor physics, but for the whole particle physics community, because it would have, of course, very intriguing consequences for any field, for cosmology, for direct LHC searches. So let's hope that they really get confirmed, and thank you very much for the attention.
Thank you, Andy. That was a great overview talk. Nothing less was expected. I think you will stay around, right? So I will give the floor now to Yuaning Gao, who is at the Peking University, who will be the discussion leader for the next 30 or so minutes. If there are questions for Andy, you can also ask them now or in the next couple of minutes. Otherwise, any other question or comment or discussion is welcome.
Okay, so it's a very nice talk, and then we can have some discussions now. Oh, Nima.
Yeah, I had a quick question. So, in the beta mu mu anomalies, the size of the effect is kind of like comparable to the standard model, right?
It's destructive, yes.
Yeah, but it's order what we get in the standard model. So
20%.
Yeah. So is it so you would think, I mean, if it's not going to be an accident that, I mean, it's not like G-2, muon G-2, for example, where the effect is coming from very heavy physics, so it's minuscule compared to the standard model. And then we have a chance of seeing it because we do an incredibly precise experiment. But there's not some sort of coincidence that the size of the new physics effect is comparable to what we have in the standard model. It's not. It's much, much smaller. And so we have to wait till we get in a position till we finally see it. Whereas here it seems like a little bit of an, it seems sort of accidental that the size of this effect from new physics is comparable to that in the standard model, unless the new particles are around at around, you know, around where the W and the Z are, which they're not. Is there some kind of picture where that coincidence is like in these in the models you were just talking about at the end?
Yeah.
As you make these new fermions and scalars heavier, I presume you have to make the size of the flavor violation in those vertices bigger, right? In order to, I mean, they're not the same as what they're not BCB or something. They must be getting larger, right?
This really depends on which model. So I think I need quite a little bit of time to answer this question. So okay. Let's start with the following. So at the anomalous magnetic moment of the muon, the deviation from G-2 already comes from photon effects. So this is why it's relatively to the standard model so incredibly small. B2S mu mu is only mediated by a W top effect. So it's clear that it's already smaller within the standard model. So if you compare the electroweak effect in G-2 to the new physics effect, it's a 100% effect, while in B2SLL, it's only a 20% effect. So if you exclude the photon, the effect you need in B2SLL is even smaller than
Sure. I agree with that, of course. Yeah. Actually, if we look at this slide of yours, I would say that the Z prime and the leptoquarks are, it would be a total coincidence that the size of the effect is comparable to that in the standard model, because it's something, for example, the Z prime is coming at tree level. I mean, it's totally different. The loop contribution has more of a chance to be comparable because they're both coming at one loop, but then it's a slightly more detailed thing that you would expect if it's making a 20% contribution to the standard model. Well, if that's not coincidental, all the particles should be around where they were in the standard model, right? And they're not there. So you have to make them heavier and also make the size of the flavor violations bigger. And then it starts looking like more of a coincidence again, not nearly as bad as in the tree level examples, but still a bit of a coincidence that the contribution you get is sort of comparable. So close, even 20% is quite close to what you get in the standard.
So, I mean, for me, the Z prime, for example, looks much more reasonable than this loop model. So, for this loop model, you already need all the one flavor violating couplings in order to accomplish them. In the Z prime model, you have a flavor symmetry to motivate them. Assume you have the U2 flavor symmetry, then this automatically gives you this gamma D to 3 of the order of VCB. This is natural, I would say, gamma D to 3 of the order of VCB. And then if you have a fundamental order 1 muon coupling for a 5 TV Z prime or 10 TV Z prime, you get naturally a 20% effect. I wouldn't say this is so bad.
Okay.
But I would totally agree
in the context of the loop models you're talking about at the end, when they're up at when the vector-like quarks are at a TeV or so, there you're jacking up the size of the flavor violating vertices, right? I mean, what is the limit? I mean, why is the you can't make them arbitrarily heavy, right? So that 2 TeV, 3 TeV limit is coming from order maxing out the size of the flavor violation?
Exactly. I mean, the flavor violation is anyway big, but I still want to have perturbative coupling.
Right. Okay. Thank you.
Thanks for the question.
Okay. Okay. I think I got one question here. And Leonardo, can you let this person ask the question himself?
Yeah, Leandro, can you come in? We've allowed you to speak.
Leandro. Okay, if not, maybe I can repeat the question here. So a question for Andrews. Thank you for the very nice talk. For the different solutions, focus, for example, on combined explanation, specific patterns of couplings are required. Could you comment on the origin of that flavor structure in the new physics sector? So Andrews, the question is clear?
I have a little bit problems understanding you, sorry.
Okay, so actually this is for the different solutions. Actually, this focus on example on combined explanations, okay? This is, they have a specific pattern of couplings. So you need to give a very specific patterns of couplings are required. So actually, this means this is a new physical sector, the flavor new structure there. Otherwise, if you want to really do this kind of, so they want to comment on why this or what kind of flavor pattern you have.
Yeah. So in all of these loop models, you just go for anarchic flavor structure. So this means you just have all the one flavor violating couplings, and so they are somehow arbitrary numbers. You roll the dice, all the one coupling, you get it. So it's completely anarchic flavor structure in all of the loop models. As I said, for the Z prime, it's really different. Here, you could motivate the structure by minimal flavor violation, or at least by a U2 cubed flavor symmetry, because the BS coupling you want for TV scale Z prime couplings is just of the order of VCB.
Okay, I think that seems to me is a perfect answer.
Thanks.
Oh, okay, so any other question? Nima, you still have questions?
No, somehow I don't. I'm a Zoom loser, and I don't know how to lower my hand. Sorry about that.
Oh,
sorry,
okay,
guys.
Actually,
sorry.
So for you other people don't have questions here. Actually, I have one. For this, okay, just this slide, you have a so-called Z2BB bar. This is kind of try to explain what happened at the left edge. This kind of forward backwards asymmetry for Z2BB bar. So could you give me a little bit more explanation? That time we know the RB actually is very accurately measured. So this new physics won't affect the RB, but give a actual contribution to AFB. What happened there?
Yeah, so this is all included in the fit. RB and AFB are included in the fit. And then here, the Q gives you a modification to right-handed ZBB coupling. And the D gives you a modification to left-handed ZBB coupling. Now, to explain the ZBB forward and backward asymmetry and RB at the same time, you need a larger effect in the right-handed coupling than in the left-handed coupling, but also a left-handed non-zero modification to the left-handed coupling is preferred at something like 2 sigma level.
Okay. Thank you. Any other questions from panelists and the audience? If not, actually, I would like to ask one more question. General
as many as you like.
to everybody here. So, I introduce new physics models to explain all these anomalies. So there must be some new predictions. Okay, I know there's some predictions could be checked or experimental tested in the future colliders or future experiments. However, one thing actually, as Bruce, at the first beginning, you ask the question: are we already fully explored the current data? Do we have any new prediction could be done with the current data, with the LHC and whatever? Actually, this new observables, especially standard model clean observables, could be checked with current data or something like that, or near future.
I think that I have one example in mind. I didn't show this here, but for example, you could have a new Higgs which couples mainly to the third generation. Then this new Higgs would maybe mostly decay to tau tau. And then I'm not sure if there exists an analysis searching for a resonance decaying to tau tau in the low energy region where you really scan over the resonance and see where it could have been.
Okay, this may be the kind of topic could be done with Day2 or something. Yeah.
I think the data is there. I don't know if anyone already did such an analysis.
Okay. Okay, now this is.
But also about to top charm. I don't know if people looked at Higgs to top chance or arbitrary masses of the resonance.
Okay, I think that's a good topic. So far, I don't think so, but this may be interesting. Okay, then we have two hands here. There's a lady first.
I think Tauhan raised hand first, so Tauhan.
You go ahead.
No,
you go ahead.
Yes, so I was just
lady first, please.
well, so I would say seniors first. Okay, so all right, so let's keep that aside for a minute. Andreas, I was just surprised with your comment about this tau searches. I would have expected them to happen for the low or the light mass Higgs, right? NMSSM like Higgs is. We should have searches for Higgs to tau.
Right.
That's an obvious candidate.
Yeah, right. I think I was confused. For the tau, they're probably there, but I think not for top charm. Is this possible?
This I have to check.
No,
I know that we have Higgs flavor violating searches for something like in the lepton channels, but I don't remember in the hadron channels.
And what I also meant, and I have to be more precise about the tau. So I meant the tau being produced from top decay. So I have a top to charm decay to Higgs, which then decays to tau. So the Higgs is only produced by a top decay.
Okay, this probably we don't have, but why would the Higgs not be produced in the classic gluon-gluon fusion or so channels in that case?
Because it's only coupling to top charm.
Oh, I'm sorry. Yes. Okay, fine. I missed that. Okay, good. So then that makes sense. Yes.
You cannot produce it from gluon fusion because it only couples to top charm, and then it decays nearly 100% to tau. And I think for such a resonance, there are no searches.
No, okay. This I can accept. Okay, fine.
Yeah, sorry, I was not precise enough.
Thanks.
Okay. Thank you. Okay, so Tao. Please.
Yeah, I have a general question about the beyond standard model of Higgs bosons, since this was brought up. Maybe the question to Nima and the others too. So so if the Higgs bosons are not too heavy to decouple, how much we should consider the Higgs bosons beyond the standard paradigm for the Z2 symmetry to keep the flavor changing neutral current away? And there have been more and more discussions to think about the out of the box to really enforce the cancellation and to allow some more general flavor structure, which means that the light Higgs boson may even couple to light generations, not directly proportional to the mass, not the minimal flavor violation type of things. So Nima was talking about the Higgs to be light, and so what do you think, Nima, and others, and how much we should not overlook the non-standard paradigm, always follow this minimal flavor violation to keep the Higgs sector to be aligned with the standard model sector. Of course, you don't have a large effect anymore. Nowadays, not only we are facing some anomalies, but we want to cross-check to see the other consequences, like the Higgs boson may be produced, may even have a significant effect with the lighter generations, may even have a Higgs to decay to light jets. Any theories to comment on the need to go beyond the standard, the Z2 paradigm to
I can make a quick comment about this. I mean, for years and years, people have gone beyond that the sort of the Weinberg-Glasgow criterion, right? Which is what you're talking about from ages ago. And the kind of beginning of the realization of approximate flavor symmetries controlling the structure of flavor changing neutral currents actually started with some very nice papers on exactly multi-Higgs doublet models, where people realized, I know the paper by Hall and Weinberg, I think, but anyway, there are others around the same time, where if you have a flavor structure that is like approximate U1 symmetries on all the generations, so that you roughly get this, that's the simplest flavor picture that gives the rough correct pattern for flavor, where the ij entry of the Yukawa matrix goes like square root of some zeta I, zeta j, where zeta is some spurion associated with each generation. Anyway, that picture already made it reasonable to have flavor changing couplings for the Higgses, but it still forced multi-TeV Higgses in order to avoid Keke bar mixing and especially, of course, epsilon ket. Then later, people talked in the context of supersymmetry, and then more generally about the U2 flavor structure and so on. So there are some non-abelian things that would be more protective. But I think in general, if you have light Higgses with any kind of any reasonable subgroup of the U3 to the 5th flavor symmetry of the standard model, which is not exactly U3 to the 5th, so you allow yourself to go beyond minimal flavor violation. Still, you would expect two large FCNCs from tree level Higgs exchange. I mean, I think that's for sure true. It's for sure true with these simple abelian kind of spurions, and I think it's also true for the U2 guys. But I don't know if there are more interesting flavor patterns that are still alive. I'll make a very obvious comment. I mean, some of the strongest constraints are, of course, in the quark sector. It's still alive. The following thing was actually still alive until sort of recently, where we got some indication of the Higgs mu coupling. It is conceivable that some of light flavor is due to the fact that they don't actually come literally from Yukawa couplings, but that you would come from couplings that look like, for example, maybe the reason the light generations are light is because the operator is not a Yukawa coupling, but is Yukawa coupling multiplied by h dagger h divided by some cutoff scale squared. And if you want to explain the light generation, for example, the muon mass that way, well, that cutoff can't be too far away because you're suppressing things by v squared over a cutoff squared. There are issues with naturalness with these ideas. If you write down that operator, you can close the h dagger h loop and get a normal Yukawa coupling, but maybe everything is wrong with naturalness, maybe. So maybe we should ignore that problem. Well, that kind of picture would lead to a huge difference in the Higgs coupling to light generations. So for instance, if literally the muon mass came from the operator which has an extra h dagger h in it, then you would expect the effective coupling of the Higgs to muons to be 3 times what it is in the standard model. And we now know that that's totally ruled out. So at most, these kind of Higgsy things can be, an order 1-ish and somewhat smaller correction to the usual Yukawas. But I think that that's perfectly alive and well for the electron. It could well be that the entire electron mass is coming not from Yukawa coupling, but from a higher dimension operator, because we don't have any indication of the Higgs coupling to electrons yet. So I think that there could be some room to, I haven't followed the literature on this subject. Maybe people have explored these sort of higher dimension operator couplings instead of Yukawa couplings for light generations. But I suspect even that is sort of very, very constrained now. But I think from there are flavor experts in the audience, I'm sure, who are much more up to date on this than I am. But I suspect that simple subgroups of U3 to the 5th do not control the FCNCs from light Higgs exchanges enough. If we wanted to imagine the Higgses are sort of light enough to produce and study at the LHC.
Mm-hmm.
Okay, thank you very much. And I see a hand from the audience. Could you let him ask questions?
Hi, Yanning. This is Ashutosh from Duke.
Okay.
Hello, and Nima. Hello, how are you?
Hey.
I may have missed it, but I didn't hear a mention of the mu to E experiment coming up at Fermilab. In the context, Yanning, your comment of upcoming experiments. If I missed it, let me know which slide or something, but I didn't hear any discussion of mu to E transition being induced by additional Higgses, higher dimension operators, things like this. Any comments?
So what I can say about why I didn't put anything about mu to E flavor violation on this slide is that in principle you really want to avoid it. So you need a symmetry which is preventing you from having it because it places so stringent bounds. So for example, this is the nice thing about this mu minus L tau symmetry, you avoid coupling to muons. But you are of course right. It gives very important bounds, and there's of course some hope that we might see it. But let me see if I have a backup slide on it. Maybe I don't. So with lepto quarks, for example, it's a very interesting story concerning mu2e flavor violation, because you either violate lepto flavor universality maximally, so you only couple to muons, or you violate lepton flavor and you produce things like mu2e gamma and mu2e conversion. So mu2e conversion can definitely help us, for example, in case it is a lepto quark, to decide what the coupling structure of it is.
Okay.
Any other questions? Okay. Not actually, I want to bring some boring questions to you guys, especially to our dissertation. So for some standard model predictions, for example, on the P5 prime, A mu, there's still kind of sizable theoretical uncertainties there. So is there any way we can reduce this uncertainty from theoretical side?
So can you still see my slides?
Yeah.
So
we can see that.
T-2, in fact, the hadronic vacuum polarization is really a problem. So you might remember this BMW-C determination of hadronic vacuum polarization. So people at the moment are using E plus E minus to hadron data together with dispersion relations to determine this contribution in T-2. But it could be calculated from first principle with the lattice. It's very difficult. This Budapest, this BMW collaboration, Budapest, Wuppertal, Mainz, they presented a first calculation of this hadronic vacuum polarization. They inflated now the errors, and the conclusion is a little bit unclear. So it goes a bit into the standard model, closer to the standard model, but it also has some tension with E plus E minus data. It's just not clear. So we need more lattice groups doing this, and of course more precise results here. For P5 prime, there's also some theory effort going on, but for me, this is not really the, let me see where it is. For me, the P5 prime problem is not really so big, because the measurement is so nicely consistent with all the other measurements that we have, that I would not guess that the origin is underestimated theory uncertainties, just because it agrees so nicely with all the other data.
Okay, any other suggestions, comments? If not, I guess, okay, this is about the time we can stop here today. So any other things from our organizer?
Yes. Thank you very much, Jörning. This was a very good session. Also, thank you, Andreas, very much for your talk and for explanations. They were very good. Thank you, everybody, for your contributions today and for the questions from the audience. I want to encourage everyone who has a comment or something they wanted to ask that was not addressed now to move to the Mattermost forum and just put the comment down. Our speakers are can have a look there, and they can answer there, and the discussion can be continued. Some interesting points were brought up earlier, for instance, by Bhupal about an accessible, also by Nima as well, an accessible list of anomalies that is being updated continuously. I think there are many things that came up that deserve to be continuously discussed. Let me close the session for now, for today, and we resume tomorrow, again at 1:30 Geneva time. And we will try tomorrow to respect a break for everybody. I think it's good to have a break in between. So thank you, everybody, again, and see you tomorrow.
Thanks a lot for organizing.
Thank you. Bye-bye.
Thank you very much. That was great fun. Thanks a lot.
Bye.
Thanks. Bye.
Bye.
Okay, so good night to most of
night.
us in
Good
the East,
morning.
and good day
Okay.
to others who are in the West.
Okay.